1. Introduction to artificial neural networks. 1.1 What are artificial neural networks? Artificial neural networks, ANNs, are a type of computational model inspired by the structure and function of the human brain. They are designed to mimic the way biological neurons process and transmit information. ANNs consist of interconnected nodes, called artificial neurons or simply neurons, which work together to perform complex computations. At its core, an artificial neural network is composed of three main components: input layer, hidden layers, and output layer. The input layer receives data or information, which is then processed through the hidden layers, and finally, the output layer produces the desired output or prediction. Each neuron in the network receives input signals, applies a mathematical transformation to them, and passes the transformed signals to the next layer of neurons. The strength of artificial neural networks lies in their ability to learn from data and make predictions or decisions based on that learning. This learning process is achieved through a training phase, where the network is exposed to a large amount of labeled data. By adjusting the weights and biases associated with each neuron, the network learns to recognize patterns and make accurate predictions. The power of artificial neural networks comes from their ability to model complex relationships and solve problems that are difficult for traditional algorithms. They excel in tasks such as pattern recognition, classification, regression, and optimization. ANNs have been successfully applied in various fields, including computer vision, natural language processing, speech recognition, finance, healthcare, and many others. 1.1.1 Structure of artificial neural networks. The structure of an artificial neural network is inspired by the interconnectedness of neurons in the human brain. The basic building block of an ANN is the artificial neuron, also known as a perceptron. A perceptron takes multiple inputs, applies weights to them, sums them up, and passes the result through an activation function to produce an output. In a typical neural network, neurons are organized into layers. The input layer receives the initial data, and the output layer produces the final output or prediction. Between the input and output layers, there can be one or more hidden layers, which perform intermediate computations. The number of hidden layers and the number of neurons in each layer can vary depending on the complexity of the problem. The connections between neurons in different layers are represented by weights. Each connection has an associated weight, which determines the strength of the connection. During the training phase, the network adjusts these weights to minimize the difference between the predicted output and the actual output. This process is known as weight optimization or learning. 1.1.2 Function of artificial neural networks. The function of artificial neural networks is to process input data and produce an output or prediction. This is achieved through a series of computations performed by the interconnected neurons. Each neuron receives input signals, applies a mathematical transformation to them, and passes the transformed signals to the next layer of neurons. The mathematical transformation applied by each neuron is determined by an activation function. The activation function introduces nonlinearity into the network, allowing it to model complex relationships between inputs and outputs. It determines whether a neuron should be activated or not based on the weighted sum of its inputs. There are various types of activation functions used in artificial neural networks, including sigmoid, tanh, ReLU, rectified linear unit, and softmax. Each activation function has its own characteristics and is suitable for different types of problems. The choice of activation function depends on the nature of the data and the desired behavior of the network. 1.1.3 Learning in artificial neural networks. Learning in artificial neural networks is achieved through a process called training. During training, the network is exposed to a large amount of labeled data, where the inputs are paired with the desired outputs. The network adjusts its weights and biases based on the difference between the predicted output and the actual output. The most commonly used learning algorithm for training artificial neural networks is called backpropagation. Backpropagation works by propagating the error from the output layer back to the hidden layers, adjusting the weights and biases along the way. This iterative process continues until the network reaches a state where the error is minimized. The training process involves two main steps: forward propagation and backward propagation. In forward propagation, the input data is fed into the network, and the output is computed layer by layer. In backward propagation, the error is calculated and propagated back through the network, updating the weights and biases. The goal of training is to minimize the difference between the predicted output and the actual output. This is achieved by adjusting the weights and biases in such a way that the network learns to recognize patterns and make accurate predictions. The training process continues until the network achieves a satisfactory level of performance. Artificial neural networks have revolutionized the field of machine learning and have become a powerful tool for solving complex problems. Their ability to learn from data and make accurate predictions has made them indispensable in various domains. In the following chapters, we will explore the history, types, applications, and advancements in artificial neural networks, providing a comprehensive understanding of this exciting field. 1.2 History of artificial neural networks. Artificial neural networks, ANNs, have a rich history that dates back several decades. The concept of ANNs was inspired by the structure and functioning of the human brain. The idea behind ANNs is to mimic the way neurons in the brain process and transmit information. Over the years, ANNs have evolved and become a powerful tool in the field of artificial intelligence and machine learning. 1.2.1 Early developments. The roots of ANS can be traced back to the 1940s and 1950s when researchers began exploring the idea of creating electronic networks that could simulate the behavior of biological neurons. One of the earliest pioneers in this field was Warren McCulloch, a neurophysiologist, and Walter Pitts, a logician. In 1943, they published a paper titled, A Logical Calculus of the Ideas Immanent in Nervous Activity, which laid the foundation for the concept of artificial neurons. In the following years, several researchers made significant contributions to the development of ANS. In 1956, John McCarthy and Marvin Minsky organized the Dartmouth Conference, which marked the birth of the field of artificial intelligence. During this conference, the idea of using ANS as a computational model gained attention. 1.2.2 Perceptrons and the neocognitron. In the late 1950s and early 1960s, Frank Rosenblatt introduced the concept of perceptrons, which are the building blocks of ANS. Perceptrons are simple models of artificial neurons that can learn from input data and make predictions. Rosenblatt's work on perceptrons laid the foundation for the development of feedforward neural networks. In the 1980s, Kunihiko Fukushima proposed the neocognitron, a hierarchical neural network model inspired by the visual system of animals. The neocognitron introduced the concept of convolutional neural networks, CNNs, which are widely used today for image recognition and computer vision tasks. 1.2.3 Backpropagation and the connectionist era. One of the most significant breakthroughs in the history of ANS came in the 1980s with the development of the backpropagation algorithm. Backpropagation is a method for training neural networks by adjusting the weights of the connections between neurons. This algorithm, first proposed by Paul Werbose in 1974 and later popularized by David Rumelhart, Geoffrey Hinton, and Ronald Williams, revolutionized the field of neural networks. The backpropagation algorithm enabled the training of deep neural networks with multiple layers, overcoming the limitations of shallow networks. This breakthrough led to the emergence of the connectionist era, where neural networks gained popularity and were applied to various domains, including pattern recognition, speech recognition, and natural language processing. 1.2.4 The AI Winter and Resurgence. Despite the initial excitement and progress in the field of ANS, the late 1980s and early 1990s witnessed a decline in interest and funding for neural networks. This period, known as the AI Winter, was characterized by a lack of significant advancements and disillusionment with the capabilities of ANS. However, in the late 2000s, there was a resurgence of interest in ANS, driven by several factors. One of the key factors was the availability of large datasets and computational power, which enabled the training of deep neural networks. Additionally, advancements in hardware, such as graphics processing units (GPUs), accelerated the training process and made it more efficient. 1.2.5 Deep Learning and Breakthrough Applications. The resurgence of ANS led to the development of deep learning, a subfield of machine learning that focuses on training deep neural networks with multiple layers. Deep learning has achieved remarkable success in various domains, including computer vision, natural language processing, and speech recognition. In 2012, AlexNet, a deep convolutional neural network, won the ImageNet Large-Scale Visual Recognition Challenge, significantly outperforming traditional computer vision techniques. This breakthrough demonstrated the power of deep learning and paved the way for numerous applications, such as autonomous vehicles, medical diagnosis, and language translation. 1.2.6 Current Trends and Future Directions. Today, ANS continue to evolve and push the boundaries of artificial intelligence. Researchers are exploring new architectures, such as recurrent neural networks (RNNs) and generative adversarial networks (GANs) to tackle complex tasks like sequence modeling and generative modeling. The future of ANS holds immense potential. Advancements in hardware, such as neuromorphic chips and quantum computing, may enable the development of even more powerful and efficient neural networks. Additionally, ethical considerations, such as bias and fairness, privacy, and transparency, are becoming increasingly important in the design and deployment of neural networks. In conclusion, the history of artificial neural networks is a story of innovation, setbacks, and resurgence. From the early developments in the 1940s to the breakthroughs in deep learning, ANS have come a long way. With ongoing research and advancements, ANS are poised to revolutionize various industries and shape the future of artificial intelligence. 1.3 Types of artificial neural networks. Artificial neural networks (ANS) are a powerful class of machine learning models inspired by the structure and function of the human brain. They consist of interconnected nodes, called neurons, which work together to process and analyze data. ANS have gained significant popularity in recent years due to their ability to learn from large amounts of data and make accurate predictions or classifications. There are several types of artificial neural networks, each designed to solve specific types of problems and excel in different domains. In this section, we will explore some of the most commonly used types of ANS and their unique characteristics. 1.3.1 Feedforward neural networks. Feedforward neural networks (FNNs) are the simplest and most basic type of artificial neural networks. They consist of multiple layers of neurons, with each neuron in a layer connected to every neuron in the subsequent layer. The information flows in one direction, from the input layer to the output layer, without any loops or feedback connections. FNNs are primarily used for tasks such as classification and regression. They are particularly effective in solving problems with well-defined inputs and outputs, where the relationship between the input and output is relatively straightforward. FNNs are widely used in various domains, including image and speech recognition, natural language processing, and financial forecasting. 1.3.2 Recurrent neural networks. Recurrent neural networks (RNNs) are designed to handle sequential data, where the order of the input elements matters. Unlike feedforward neural networks, RNNs have feedback connections, allowing information to flow in loops. This enables RNNs to capture temporal dependencies and process sequences of arbitrary length. RNNs are widely used in tasks such as speech recognition, language modeling, and machine translation. They excel in tasks that require understanding and generating sequences, as they can maintain an internal memory of past inputs. However, traditional RNNs suffer from the vanishing gradient problem, which limits their ability to capture long-term dependencies. To overcome this limitation, variants of RNNs, such as long short-term memory (LSTM) and gated recurrent unit (GRU), have been developed. 1.3.3 Convolutional neural networks. Convolutional neural networks (CNNs) are specifically designed for processing grid-like data, such as images or time series. They are inspired by the visual cortex of the human brain and consist of multiple layers of interconnected neurons. CNNs use convolutional layers to automatically learn hierarchical representations of the input data, capturing local patterns and spatial relationships. CNNs have revolutionized the field of computer vision and achieved remarkable success in tasks such as image classification, object detection, and image segmentation. They are known for their ability to extract meaningful features from raw pixel data, enabling them to understand and interpret visual information effectively. 1.3.4 Generative adversarial networks. Generative adversarial networks (GANs) are a unique type of neural network architecture that consists of two components, a generator and a discriminator. The generator generates synthetic data samples, while the discriminator tries to distinguish between real and fake samples. The two components are trained simultaneously, with the generator aiming to generate increasingly realistic samples, and the discriminator trying to improve its ability to differentiate between real and fake samples. GANs have gained significant attention in recent years for their ability to generate highly realistic and diverse synthetic data. They have been successfully applied in various domains, including image synthesis, text generation, and music composition. GANs have the potential to revolutionize the field of creative content generation and have opened up new possibilities for artists and designers. 1.3.5 Reinforcement learning in neural networks. Reinforcement learning (RL) is a branch of machine learning that focuses on training agents to make sequential decisions in an environment to maximize a reward signal. Neural networks are often used as function approximators in RL algorithms to learn complex policies. Deep Q networks (DQNs) are a popular class of RL algorithms that use deep neural networks to approximate the action value function. DQNs have achieved remarkable success in challenging tasks, such as playing Atari games and mastering complex board games like Go and chess. RL with neural networks has applications in various domains, including robotics, autonomous vehicles, and game playing. It enables agents to learn from experience and make intelligent decisions in dynamic and uncertain environments. Conclusion. In this section, we explored some of the most commonly used types of artificial neural networks. Feedforward neural networks are suitable for tasks with well-defined inputs and outputs, while recurrent neural networks excel in processing sequential data. Convolutional neural networks are specifically designed for grid-like data, such as images, and have revolutionized computer vision tasks. Generative adversarial networks have the unique ability to generate realistic synthetic data. Finally, reinforcement learning with neural networks enables agents to learn from experience and make intelligent decisions in dynamic environments. Each type of neural network has its own strengths and applications, making them powerful tools in the field of machine learning and artificial intelligence. 1.4 Applications of artificial neural networks. Artificial neural networks (ANNs) have gained significant popularity and have found numerous applications across various fields. These powerful computational models have the ability to learn and make predictions based on patterns and relationships in data. In this section, we will explore some of the key applications of artificial neural networks. 1.4.1 Pattern recognition and image processing. One of the most prominent applications of artificial neural networks is in the field of pattern recognition and image processing. ANNs have been successfully used for tasks such as object detection, image classification, and facial recognition. By training a neural network on a large dataset of images, it can learn to identify and classify objects with a high degree of accuracy. This has found applications in areas such as medical imaging, surveillance systems, and autonomous vehicles. 1.4.2 Natural language processing. Artificial neural networks have revolutionized the field of natural language processing (NLP). NLP involves the interaction between computers and human language, enabling machines to understand, interpret, and generate human language. ANNs, particularly recurrent neural networks (RNNs) and transformer models, have been instrumental in tasks such as language translation, sentiment analysis, text generation, and speech recognition. These applications have greatly improved the efficiency and accuracy of language-related tasks, making them essential in areas like chatbots, virtual assistants, and language translation services. 1.4.3 Financial forecasting and stock market prediction. Artificial neural networks have proven to be valuable tools in the field of finance. They have been extensively used for financial forecasting, stock market prediction, and algorithmic trading. By analyzing historical financial data, ANS can identify patterns and trends, enabling them to make predictions about future market movements. This has been particularly useful for traders and investors in making informed decisions and managing risks. 1.4.4 Medical diagnosis and healthcare. The healthcare industry has greatly benefited from the application of artificial neural networks. ANS have been used for medical diagnosis, disease prediction, and treatment planning. By training on large datasets of medical records and patient data, neural networks can learn to identify patterns and make accurate predictions about diseases and conditions. This has led to advancements in areas such as cancer detection, medical imaging analysis, and personalized medicine. 1.4.5 Autonomous vehicles. Artificial neural networks play a crucial role in the development of autonomous vehicles. They are used for tasks such as object detection, lane recognition, and decision-making. By processing data from various sensors, such as cameras and lidar, neural networks can analyze the environment and make real-time decisions to ensure safe and efficient navigation. The ability of ANS to learn from experience and adapt to changing conditions makes them essential in the development of self-driving cars and other autonomous systems. 1.4.6 Fraud detection and cybersecurity. Artificial neural networks have proven to be effective in detecting fraudulent activities and enhancing cybersecurity. By analyzing large volumes of data, ANS can identify patterns and anomalies that indicate potential fraud or security breaches. This has applications in areas such as credit card fraud detection, network intrusion detection, and malware detection. Neural networks can learn from past incidents and continuously improve their ability to detect and prevent fraudulent activities, making them valuable tools in maintaining the security of systems and networks. 1.4.7 Industrial automation and predictive maintenance. Artificial neural networks have found applications in industrial automation and predictive maintenance. By analyzing sensor data from machines and equipment, ANS can predict failures and maintenance needs, allowing for proactive maintenance and minimizing downtime. This has significant implications for industries such as manufacturing, energy, and transportation, where the efficient operation of machinery is crucial. 1.4.8 Gaming and virtual reality. Artificial neural networks have also made their way into the gaming and virtual reality (VR) industry. They have been used for tasks such as game playing, character animation, and virtual environment generation. Neural networks can learn from gameplay data and develop strategies to compete against human players or provide realistic and interactive virtual environments. This has enhanced the gaming experience and opened up new possibilities in the field of VR. These are just a few examples of the wide range of applications of artificial neural networks. As the field continues to advance, we can expect to see even more innovative and impactful uses of this powerful technology in various domains. The versatility and adaptability of neural networks make them a valuable tool for solving complex problems and driving advancements in science, technology, and society as a whole. 2. Neurons and activation functions. 2.1 Structure and function of neurons. Artificial neural networks are inspired by the structure and function of biological neurons in the human brain. In this section, we will explore the fundamental building blocks of neural networks, known as neurons, and understand how they work together to process and transmit information. 2.1.1 Neuron anatomy. A neuron is a specialized cell that is responsible for receiving, processing, and transmitting electrical signals in the brain. Similarly, in artificial neural networks, a neuron, also known as a node or a perceptron, is a fundamental unit that performs computations. The structure of a neuron consists of three main components. Dendrites. Dendrites are the input branches of a neuron that receive signals from other neurons or external sources. These signals, represented as numerical values, are transmitted through the dendrites and combined at the neuron's cell body. Cell body, soma. The cell body is the central part of the neuron that processes the incoming signals. It performs computations on the received inputs and generates an output signal. Axon. The axon is the output branch of the neuron that transmits the processed signal to other neurons or external devices. The axon can be thought of as a long cable that carries the electrical signal away from the cell body. 2.1.2 Neuron function. The function of a neuron is to process the incoming signals and generate an output signal based on a specific rule or activation function. The activation function determines whether the neuron should fire or remain inactive based on the inputs it receives. The process of signal transmission in a neuron can be summarized in the following steps. Signal integration. The dendrites receive signals from other neurons or external sources. These signals are combined at the cell body, where they are summed together. Activation. The summed input signals are then passed through the activation function. The activation function introduces nonlinearity into the neuron's output, allowing it to model complex relationships between inputs and outputs. Output generation. The activation function produces an output signal based on the result of the activation. This output signal is then transmitted through the axon to other neurons or external devices. 2.1.3 Activation functions. The choice of activation function plays a crucial role in determining the behavior and learning capabilities of a neural network. Different activation functions introduce different nonlinearities, which enable neural networks to model complex patterns and make accurate predictions. There are several commonly used activation functions in neural networks. Step function. The step function is a simple activation function that outputs a binary value based on a threshold. If the input is above the threshold, the output is set to 1, otherwise, it is set to 0. This function is primarily used in binary classification problems. Sigmoid function. The sigmoid function is a smooth, S-shaped curve that maps the input to a value between 0 and 1. It is widely used in neural networks as it provides a smooth transition between the two extremes. The sigmoid function is particularly useful in problems where the output needs to be interpreted as a probability. ReLU rectified linear unit function. The ReLU function is a piecewise linear function that outputs the input directly if it is positive, and 0 otherwise. It is computationally efficient and helps alleviate the vanishing gradient problem, which can occur during training. ReLU is commonly used in deep neural networks. tanh function. The hyperbolic tangent tanh function is similar to the sigmoid function but maps the input to a value between -1 and 1. It is symmetric around the origin and is useful in problems where the output needs to be centered around 0. 2.1.4 Neuron networks and layers. In a neural network, neurons are organized into layers. The most common types of layers are the input layer, hidden layers, and output layer. The input layer receives the initial input data, and the output layer produces the final output of the network. The hidden layers, as the name suggests, are located between the input and output layers and perform intermediate computations. The number of neurons in each layer and the connections between them determine the network's architecture and its learning capabilities. The connections between neurons are represented by weights, which determine the strength of the signal transmitted from one neuron to another. Neural networks can have multiple hidden layers, making them deep neural networks. Deep neural networks have the ability to learn complex representations and extract high-level features from the input data. In summary, neurons are the fundamental building blocks of artificial neural networks. They receive input signals, process them using activation functions, and generate output signals. The organization of neurons into layers and the choice of activation functions play a crucial role in the network's ability to learn and make accurate predictions. 2.2 Activation functions in neural networks. Activation functions play a crucial role in artificial neural networks by introducing nonlinearity to the network's output. They determine the output of a neuron based on the weighted sum of its inputs. In other words, activation functions decide whether a neuron should be activated or not, and to what extent. The choice of activation function is important as it directly affects the network's ability to learn and make accurate predictions. Different activation functions have different properties, and understanding their characteristics is essential for designing effective neural networks. 2.2.1 Linear activation function. The linear activation function, also known as the identity function, is the simplest activation function. It computes the weighted sum of the inputs without applying any nonlinearity. The output of a neuron with a linear activation function is directly proportional to the input. While linear activation functions are straightforward and easy to compute, they have limited expressive power. Neural networks with only linear activation functions can only learn linear relationships between inputs and outputs. This limitation makes linear activation functions less suitable for complex tasks that require nonlinear mappings. 2.2.2 Step activation function. The step activation function, also known as the Heaviside step function, is a binary activation function. It assigns a value of 1 if the input is greater than or equal to a threshold, and 0 otherwise. The step function is useful for binary classification problems where the output needs to be either 0 or 1. However, the step function is not differentiable, which poses challenges for gradient-based optimization algorithms used in training neural networks. The lack of differentiability prevents the use of backpropagation, a popular algorithm for updating the weights of neural networks. As a result, the step function is rarely used in modern neural networks. 2.2.3 Sigmoid activation function. The sigmoid activation function is a smooth, S-shaped curve that maps the input to a value between 0 and 1. It is defined as sigmoid x equals 1, 1 plus express x. The sigmoid function is widely used in neural networks, especially in the early days of deep learning. It has the desirable property of being differentiable, which allows for efficient gradient-based optimization. The sigmoid function is particularly useful in binary classification problems where the output needs to be interpreted as a probability. However, the sigmoid function suffers from the vanishing gradient problem. As the input to the sigmoid function becomes very large or very small, the gradient approaches 0, making it difficult for the network to learn. This limitation led to the development of alternative activation functions that address the vanishing gradient problem. 2.2.4 Hyperbolic tangent tanh activation function. The hyperbolic tangent tanh activation function is similar to the sigmoid function but maps the input to a value between -1 and 1. It is defined as tanh x equals express x plus express x. Like the sigmoid function, the tanh function is differentiable and suitable for gradient-based optimization. It is commonly used in neural networks, especially in the hidden layers. The tanh function has the advantage of being zero-centered, which helps in the convergence of the optimization process. However, the tanh function still suffers from the vanishing gradient problem, especially for inputs far from zero. This limitation led to the development of activation functions that alleviate the vanishing gradient problem while maintaining nonlinearity. 2.2.5 Rectified linear unit, ReLU, activation function. The rectified linear unit, ReLU, activation function is a piecewise linear function that outputs the input if it is positive, and zero otherwise. It is defined as ReLU x equals max 0, x. ReLU has gained popularity in recent years due to its simplicity and effectiveness. It overcomes the vanishing gradient problem by providing a non-zero gradient for positive inputs. The ReLU function is computationally efficient and allows neural networks to learn complex representations. However, ReLU suffers from a drawback known as the dying ReLU problem. Neurons with negative inputs become inactive and stop learning, resulting in dead neurons. To address this issue, variants of ReLU, such as leaky ReLU and parametric ReLU, have been proposed. 2.2.6 Other activation functions. In addition to the activation functions mentioned above, there are several other activation functions that have been proposed and used in neural networks. Some of these include exponential linear unit ELU. ELU is similar to ReLU but has a smooth curve for negative inputs, which helps alleviate the dying ReLU problem. Softmax activation function. Softmax is commonly used in the output layer of neural networks for multi-class classification problems. It normalizes the outputs to represent class probabilities. Swish activation function. Swish is a recently proposed activation function that combines the nonlinearity of ReLU with a smooth curve. It has shown promising results in improving the performance of neural networks. The choice of activation function depends on the specific task and the characteristics of the data. Experimentation and empirical evaluation are often necessary to determine the most suitable activation function for a given problem. 2.3 Choosing the right activation function. In artificial neural networks, the activation function plays a crucial role in determining the output of a neuron. It introduces nonlinearity into the network, allowing it to learn complex patterns and make accurate predictions. The choice of activation function can significantly impact the performance and convergence of the neural network. In this section, we will explore the factors to consider when selecting the right activation function for a given task. 2.3.1 Nonlinearity and differentiability. One of the primary considerations when choosing an activation function is its ability to introduce nonlinearity into the network. Linear activation functions, such as the identity function, do not introduce nonlinearity and limit the expressive power of the neural network. Nonlinear activation functions, on the other hand, enable the network to learn complex relationships between inputs and outputs. Another important aspect to consider is the differentiability of the activation function. Differentiability is crucial for training neural networks using gradient-based optimization algorithms, such as backpropagation. The ability to compute derivatives allows the network to update its weights and biases efficiently. Therefore, it is essential to choose an activation function that is differentiable, or at least has a well-defined derivative almost everywhere. 2.3.2 Activation function characteristics. Different activation functions have distinct characteristics that make them suitable for specific tasks. Let's explore some of the commonly used activation functions and their properties. 2.3.2.1 Sigmoid activation function. The sigmoid activation function, also known as the logistic function, is a popular choice for binary classification problems. It maps the input to a value between 0 and 1, which can be interpreted as the probability of belonging to a particular class. The sigmoid function has a smooth and bounded output, making it suitable for models that require probabilistic interpretations. However, the sigmoid function suffers from the vanishing gradient problem. As the input moves away from 0, the gradient of the sigmoid function becomes close to 0, leading to slow convergence during training. This limitation makes the sigmoid function less suitable for deep neural networks. 2.3.2.2 Hyperbolic tangent tanh activation function. The hyperbolic tangent function, or tanh, is another commonly used activation function. It is similar to the sigmoid function but maps the input to a value between -1 and 1. Like the sigmoid function, tanh is also smooth and bounded, making it suitable for classification tasks. The tanh function addresses the vanishing gradient problem to some extent compared to the sigmoid function. It has steeper gradients around 0, allowing for faster convergence during training. However, the vanishing gradient problem still persists as the input moves away from 0. 2.3.2.3 Rectified linear unit, ReLU, activation function. The rectified linear unit, ReLU, activation function has gained popularity in recent years, especially in deep learning. It is defined as the maximum of 0 in the input value. ReLU provides a simple and computationally efficient activation function that overcomes the vanishing gradient problem. ReLU has a nonlinear nature and does not suffer from saturation, unlike sigmoid and tanh functions. It allows the network to learn faster and can handle sparse and high-dimensional data effectively. However, ReLU can also suffer from the dying ReLU problem, where some neurons become inactive and never recover during training. 2.3.2.4 Leaky ReLU and Parametric ReLU (PRELU). To address the dying ReLU problem, variations of the ReLU activation function have been introduced. Leaky ReLU introduces a small slope for negative inputs, allowing some gradient flow even for negative values. Parametric ReLU (PRELU) takes this idea further by making the slope a learnable parameter. Leaky ReLU and PRELU have shown improved performance in deep neural networks compared to the standard ReLU function. They help mitigate the dying ReLU problem and provide better gradient flow during training. 2.3.3 Task-specific considerations. The choice of activation function should also consider the specific requirements of the task at hand. Here are a few task-specific considerations. 2.3.3.1 Binary classification. For binary classification tasks, the sigmoid activation function is often a suitable choice. It maps the output to a probability between 0 and 1, allowing for easy interpretation and decision-making. 2.3.3.2 Multiclass classification. For multiclass classification tasks, the softmax activation function is commonly used. It normalizes the outputs into a probability distribution over multiple classes, enabling the model to make predictions for each class independently. 2.3.3.3 Regression. For regression tasks, where the goal is to predict continuous values, linear activation functions or their variants, such as the identity function or the ReLU function, can be used. 2.3.3.4 Time series analysis. For time series analysis tasks, recurrent neural networks (RNNs) with activation functions like the hyperbolic tangent (tanh) or the rectified linear unit (ReLU) are often employed. These activation functions allow the network to capture temporal dependencies effectively. 2.3.4 Experimentation and model evaluation. Choosing the right activation function often involves experimentation and model evaluation. It is essential to try different activation functions and compare their performance on validation or test datasets. The choice of activation function can have a significant impact on the model's accuracy, convergence speed, and generalization ability. In conclusion, selecting the right activation function is a critical decision when designing neural networks. It involves considering factors such as nonlinearity, differentiability, and task-specific requirements. By understanding the characteristics of different activation functions and experimenting with them, one can optimize the performance of neural networks for a wide range of tasks. 2.4 Common activation functions. Activation functions play a crucial role in artificial neural networks by introducing nonlinearity to the network's output. They determine the output of a neuron based on the weighted sum of its inputs. In this section, we will explore some of the most commonly used activation functions in neural networks and understand their properties and applications. 2.4.1 Sigmoid activation function. The sigmoid activation function, also known as the logistic function, is one of the earliest and most widely used activation functions in neural networks. It takes a real valued input and maps it to a value between 0 and 1. The sigmoid function is defined as f(x) equals 1, 1 plus express x. The sigmoid function has a smooth S-shaped curve, which makes it suitable for models that require a probabilistic interpretation. It is commonly used in binary classification problems, where the output represents the probability of belonging to a particular class. However, the sigmoid function suffers from the vanishing gradient problem, where the gradient becomes very small for extreme input values, leading to slow convergence during training. 2.4.2 Hyperbolic tangent (tanh) activation function. The hyperbolic tangent activation function, also known as the tanh function, is similar to the sigmoid function but maps the input to a value between -1 and 1. The tanh function is defined as f(x) equals express x express x express x plus express x. Like the sigmoid function, the tanh function is also smooth and nonlinear. It is commonly used in neural networks for classification tasks, especially when the output needs to be centered around 0. The tanh function addresses the vanishing gradient problem to some extent compared to the sigmoid function. However, it still suffers from the saturation problem, where the output saturates at the extremes, leading to slower learning. 2.4.3 Rectified linear unit (ReLU) activation function. The rectified linear unit (ReLU) activation function is a popular choice in deep neural networks due to its simplicity and effectiveness. It is defined as f(x) equals max 0, x. The ReLU function returns the input value if it is positive and 0 otherwise. This activation function introduces sparsity in the network by setting negative values to 0, which can help in reducing overfitting. ReLU is computationally efficient and allows for faster training compared to sigmoid and tanh functions. However, ReLU suffers from the dying ReLU problem, where neurons can become dead and stop learning if they consistently output 0. To address this issue, variants of ReLU, such as leaky ReLU and parametric ReLU, have been proposed. 2.4.4 Softmax activation function. The softmax activation function is commonly used in multi-class classification problems, where the output represents the probability distribution over multiple classes. It takes a vector of real-valued inputs and normalizes them to sum up to 1. The softmax function is defined as f x underscore I equals express x underscore I sum express x underscore j. The softmax function ensures that the output probabilities are positive and sum up to 1, making it suitable for multi-class classification tasks. It is often used in the output layer of neural networks, combined with the cross-entropy loss function. The softmax function is differentiable, allowing for efficient gradient-based optimization during training. 2.4.5 Other activation functions. Apart from the commonly used activation functions mentioned above, there are several other activation functions that have been proposed and used in neural networks. Some of these include linear activation function. The linear activation function simply returns the input value as the output. It is commonly used in regression tasks where the output needs to be a continuous value. Exponential linear unit (ELU). The ELU activation function is a variant of ReLU that introduces a small negative slope for negative inputs, which helps alleviate the dying ReLU problem. Scaled exponential linear unit (SELU). The SELU activation function is a self-normalizing variant of the ELU function that ensures the mean and variance of the output remain constant across layers, leading to more stable training. Gaussian error linear unit (JELU). The JELU activation function is a smooth approximation of the rectifier function and has been shown to improve the performance of deep neural networks, especially in natural language processing tasks. The choice of activation function depends on the specific problem at hand and the characteristics of the data. Experimentation and empirical evaluation are often necessary to determine the most suitable activation function for a given task. In the next chapter, we will delve into feedforward neural networks, which are the foundation of many modern neural network architectures. We will explore their architecture, training algorithms, and techniques for improving their performance. 3. Feedforward neural networks. 3.1 Architecture of feedforward neural networks. Feedforward neural networks, also known as multilayer perceptrons (MLPs), are one of the most common types of artificial neural networks. They are widely used in various fields, including image recognition, natural language processing, and financial forecasting. In this section, we will explore the architecture of feedforward neural networks and understand how they process information. 3.1.1 Structure of feedforward neural networks. The architecture of a feedforward neural network consists of an input layer, one or more hidden layers, and an output layer. Each layer is composed of multiple interconnected artificial neurons, also known as nodes or units. The connections between the neurons are represented by weights, which determine the strength of the signal transmitted between them. The input layer is responsible for receiving the input data, which could be numerical values, images, or text. Each neuron in the input layer corresponds to a feature or attribute of the input data. For example, in an image recognition task, each neuron in the input layer may represent a pixel value. The hidden layers are intermediate layers between the input and output layers. They perform complex computations and extract relevant features from the input data. Each neuron in the hidden layers receives inputs from all the neurons in the previous layer and calculates a weighted sum of these inputs. This sum is then passed through an activation function, which introduces nonlinearity into the network. The output layer produces the final result or prediction based on the processed information from the hidden layers. The number of neurons in the output layer depends on the nature of the problem. For example, in a binary classification task, there would be 2 neurons in the output layer, representing the probabilities of the 2 classes. 3.1.2 Forward propagation. The process of information flow in a feedforward neural network is called forward propagation. It involves passing the input data through the network and calculating the output. Each neuron in the network receives inputs from the neurons in the previous layer, multiplies them by their corresponding weights, and applies an activation function to the weighted sum. The weighted sum of inputs in a neuron is calculated using the following formula. Weighted underscore sum equals input underscore 1 asterisk weight underscore 1 plus input underscore 2 asterisk weight underscore 2 plus input underscore n asterisk weight underscore n. The activation function introduces nonlinearity into the network and determines the output of each neuron. Common activation functions include the sigmoid function, the hyperbolic tangent function, and the rectified linear unit (ReLU) function. The choice of activation function depends on the nature of the problem and the desired properties of the network. The output of each neuron in the hidden layers becomes the input for the neurons in the next layer. This process continues until the output layer is reached, and the final result or prediction is obtained. 3.1.3 Training feedforward neural networks. Training a feedforward neural network involves adjusting the weights of the connections between the neurons to minimize the difference between the predicted output and the actual output. This process is known as supervised learning and is typically done using a technique called backpropagation. Backpropagation is an iterative process that involves 2 main steps: forward propagation and backward propagation of errors. In the forward propagation step, the input data is passed through the network, and the output is calculated. The difference between the predicted output and the actual output, known as the error, is then calculated. In the backward propagation step, the error is propagated back through the network, and the weights are adjusted accordingly. This is done by calculating the gradient of the error with respect to each weight using the chain rule of calculus. The weights are then updated in the opposite direction of the gradient, which helps in minimizing the error. The process of forward and backward propagation is repeated for multiple iterations or epochs until the network converges to a satisfactory level of accuracy. During training, the network learns to recognize patterns and make accurate predictions based on the provided training data. 3.1.4 Overfitting and underfitting. One challenge in training feedforward neural networks is finding the right balance between overfitting and underfitting. Overfitting occurs when the network performs well on the training data but fails to generalize to new, unseen data. This happens when the network becomes too complex and starts to memorize the training examples instead of learning the underlying patterns. Underfitting, on the other hand, occurs when the network is too simple and fails to capture the complexity of the data. This results in poor performance on both the training and test data. To address these issues, various techniques can be used, such as regularization, early stopping, and cross-validation. Regularization techniques, such as L1 and L2 regularization, help in preventing overfitting by adding a penalty term to the loss function. This penalty term discourages the network from assigning too much importance to any particular weight. Early stopping involves stopping the training process when the performance on the validation set starts to deteriorate, thus preventing overfitting. Cross-validation is a technique used to evaluate the performance of the network on multiple subsets of the data. It helps in estimating the generalization error and provides insights into the network's ability to perform well on unseen data. In conclusion, feedforward neural networks are a fundamental type of artificial neural network architecture. They consist of multiple layers of interconnected neurons and are trained using forward and backward propagation. Understanding the architecture and training process of feedforward neural networks is crucial for building and optimizing neural network models for various applications. 3.2 Training feedforward neural networks. Training feedforward neural networks is a crucial step in harnessing the power of artificial neural networks. It involves the process of adjusting the weights and biases of the network to optimize its performance and improve its ability to make accurate predictions. In this section, we will explore the various techniques and algorithms used to train feedforward neural networks. 3.2.1 Supervised learning. Supervised learning is the most common approach to training feedforward neural networks. It involves providing the network with a labeled dataset, where each input is associated with a corresponding target output. The network learns to map the inputs to the correct outputs by adjusting its weights and biases through an iterative process. The training process begins with initializing the weights and biases randomly. The network then goes through a series of forward and backward passes to compute the output and update the weights, respectively. During the forward pass, the inputs are propagated through the network, and the output is calculated using the current weights and biases. The difference between the predicted output and the target output is measured using a loss function, such as mean squared error or cross-entropy. The backward pass, also known as backpropagation, is the key step in training feedforward neural networks. It involves calculating the gradients of the loss function with respect to the weights and biases of the network. These gradients indicate the direction and magnitude of the weight and bias updates required to minimize the loss function. 3.2.2 Backpropagation algorithm. The backpropagation algorithm is the cornerstone of training feedforward neural networks. It efficiently computes the gradients of the loss function with respect to the weights and biases by propagating the errors backward through the network. The algorithm consists of two main steps, the forward pass and the backward pass. During the forward pass, the inputs are propagated through the network layer by layer, and the output is calculated. The calculated output is then compared to the target output, and the error is computed using the chosen loss function. In the backward pass, the error is propagated backward through the network, starting from the output layer. The gradients of the loss function with respect to the weights and biases are calculated using the chain rule of calculus. These gradients are then used to update the weights and biases of the network, iteratively improving its performance. The backpropagation algorithm is computationally efficient because it calculates the gradients layer by layer, avoiding redundant computations. It allows the network to learn complex patterns and relationships in the data by adjusting the weights and biases based on the error signals propagated backward. 3.2.3 Gradient descent optimization. Gradient descent is a widely used optimization algorithm for training feedforward neural networks. It iteratively adjusts the weights and biases of the network in the direction of steepest descent of the loss function. The basic idea behind gradient descent is to update the weights and biases by subtracting a fraction of the gradients from their current values. This fraction is known as the learning rate, and it determines the step size taken in each iteration. A smaller learning rate results in slower convergence but can help avoid overshooting the optimal solution, while a larger learning rate can lead to faster convergence but may cause instability. There are different variants of gradient descent, such as batch gradient descent, stochastic gradient descent, and mini-batch gradient descent. In batch gradient descent, the gradients are calculated using the entire training dataset. Stochastic gradient descent, on the other hand, computes the gradients for each training example individually. Mini-batch gradient descent strikes a balance by computing the gradients for a small subset of the training data at a time. 3.2.4 Regularization techniques. Regularization techniques are used to prevent overfitting and improve the generalization ability of feedforward neural networks. Overfitting occurs when the network performs well on the training data but fails to generalize to unseen data. One common regularization technique is L2 regularization, also known as weight decay. It adds a penalty term to the loss function that discourages large weights. This helps prevent the network from relying too heavily on a few input features and encourages it to learn more robust representations. Another regularization technique is dropout. Dropout randomly sets a fraction of the activations in each layer to 0 during training. This forces the network to learn redundant representations and reduces the reliance on specific neurons, making the network more robust to noise and overfitting. 3.2.5 Hyperparameter tuning. Hyperparameter tuning is the process of finding the optimal values for the hyperparameters of a feedforward neural network. Hyperparameters are parameters that are not learned during training but are set before the training process begins. Some important hyperparameters include the learning rate, the number of hidden layers, the number of neurons in each layer, the activation function, and the regularization strength. Finding the right combination of hyperparameters is crucial for achieving good performance and preventing issues like underfitting or overfitting. Hyperparameter tuning can be done manually by trying different combinations and evaluating the performance on a validation set. However, this approach can be time-consuming and inefficient. Alternatively, automated techniques such as grid search, random search, or Bayesian optimization can be used to explore the hyperparameter space more efficiently. In conclusion, training feedforward neural networks involves using supervised learning techniques, such as backpropagation, to adjust the weights and biases of the network. Gradient descent optimization is commonly used to update the weights and biases iteratively. Regularization techniques help prevent overfitting, and hyperparameter tuning is essential for finding the optimal configuration of the network. By mastering the training process, we can unlock the full potential of feedforward neural networks and leverage their power in various applications. 3.3 Backpropagation algorithm. The backpropagation algorithm is a fundamental technique used in training feedforward neural networks. It is an iterative process that allows the network to learn from its mistakes and adjust its weights and biases accordingly. Backpropagation is based on the concept of gradient descent, which aims to minimize the error between the network's predicted output and the actual output. 3.3.1 Understanding backpropagation. Backpropagation works by propagating the error backwards through the network, hence the name. It calculates the gradient of the error function with respect to each weight and bias in the network, and then updates these parameters in the opposite direction of the gradient to minimize the error. The process of backpropagation can be broken down into several steps. Forward pass. During the forward pass, the input data is fed into the network, and the activations of each neuron are calculated layer by layer until the output is obtained. This involves applying the activation function to the weighted sum of the inputs for each neuron. Error calculation. Once the output is obtained, the error between the predicted output and the actual output is calculated using a suitable error function, such as mean-squared error or cross-entropy loss. Backward pass. In the backward pass, the error is propagated back through the network. Starting from the output layer, the gradient of the error with respect to the activations of the neurons in each layer is calculated. This is done using the chain rule of calculus, which allows us to calculate the derivative of a composite function. Weight and bias update. After calculating the gradients, the weights and biases of the network are updated using an optimization algorithm, such as stochastic gradient descent (SGD) or ADAM. The update rule involves multiplying the gradient by a learning rate and subtracting it from the current value of the weight or bias. Repeat. Steps 1 to 4 are repeated for a specified number of iterations or until the network converges to a satisfactory level of performance. 3.3.2 The chain rule and gradient calculation. The key to the backpropagation algorithm lies in the calculation of the gradients using the chain rule. The chain rule allows us to compute the derivative of a composite function by multiplying the derivatives of its individual components. In the context of neural networks, the chain rule is used to calculate the gradient of the error with respect to the weights and biases in each layer. This gradient is then used to update the parameters during the weight and bias update step. To understand the chain rule, let's consider a simple example. Suppose we have a neural network with two layers, an input layer and an output layer. The output of the network is given by output equals activation underscore function, weights asterisk inputs plus bias. To calculate the gradient of the error with respect to the weights, we need to compute the partial derivative of the error with respect to the output with respect to the weighted sum, and the weighted sum with respect to the weights. By applying the chain rule, we can express the gradient of the error with respect to the weights as gradient underscore weights equals gradient underscore error asterisk gradient underscore output asterisk gradient underscore weighted underscore sum. The gradient underscore error represents the derivative of the error with respect to the output. The gradient underscore output represents the derivative of the output with respect to the weighted sum, and the gradient underscore weighted underscore sum represents the derivative of the weighted sum with respect to the weights. 3.3.3 Overcoming challenges in backpropagation. While backpropagation is a powerful algorithm for training neural networks, it is not without its challenges. Some of the common challenges faced in backpropagation include vanishing and exploding gradients. In deep neural networks, the gradients can become very small or very large as they are propagated backward through the layers. This can lead to slow convergence or instability in the training process. Techniques such as weight initialization, gradient clipping, and batch normalization are used to mitigate these issues. Local minima. Backpropagation relies on gradient descent to find the optimal values for the weights and biases. However, it is possible for the algorithm to get stuck in local minima, where the error cannot be further reduced. Techniques such as momentum, learning rate scheduling, and adaptive optimization algorithms help overcome this problem. Overfitting. Backpropagation can sometimes lead to overfitting, where the network performs well on the training data but fails to generalize to unseen data. Regularization techniques, such as L1 and L2 regularization, dropout, and early stopping, are used to prevent overfitting and improve the generalization ability of the network. Despite these challenges, backpropagation remains a widely used and effective algorithm for training neural networks. It has played a crucial role in the success of deep learning and has enabled the development of sophisticated models that can solve complex problems across various domains. In the next section, we will explore techniques for improving the performance of feedforward neural networks, including regularization, optimization algorithms, and hyperparameter tuning. Summary. The backpropagation algorithm is a key component in training feedforward neural networks. It allows the network to learn from its mistakes by propagating the error backwards through the layers and updating the weights and biases accordingly. The algorithm relies on the chain rule to calculate the gradients, which are then used to update the parameters during the weight and bias update step. Despite its challenges, backpropagation has been instrumental in the success of neural networks and has paved the way for advancements in deep learning. 3.4 Improving feedforward neural networks. Feedforward neural networks have proven to be powerful tools for solving complex problems in various domains. However, like any other machine learning model, they are not without their limitations. In this section, we will explore some techniques and strategies to improve the performance and effectiveness of feedforward neural networks. 3.4.1 Regularization techniques. Overfitting is a common problem in neural networks, where the model becomes too complex and starts to memorize the training data instead of learning the underlying patterns. Regularization techniques help prevent overfitting and improve the generalization ability of the network. 3.4.1.1 L1 and L2 regularization. L1 and L2 regularization are two commonly used techniques to add a penalty term to the loss function during training. L1 regularization encourages sparsity in the weights by adding the absolute values of the weights to the loss function. On the other hand, L2 regularization, also known as weight decay, adds the squared values of the weights to the loss function. Both techniques help prevent the weights from becoming too large and promote simpler models. 3.4.1.2 Dropout. Dropout is a regularization technique that randomly sets a fraction of the input units to 0 during each training iteration. This helps prevent the network from relying too heavily on any single input feature and encourages the network to learn more robust and generalizable representations. Dropout has been shown to be effective in reducing overfitting and improving the performance of neural networks. 3.4.2 Optimizing the learning rate. The learning rate is a crucial hyperparameter that determines the step size at which the model updates its weights during training. Choosing an appropriate learning rate is essential for achieving good performance in neural networks. 3.4.2.1 Learning rate scheduling. Learning rate scheduling involves adjusting the learning rate during training to improve convergence and prevent overshooting or getting stuck in local minima. One common approach is to start with a higher learning rate and gradually decrease it over time. This allows the model to make larger updates in the beginning when the weights are far from the optimal values and make smaller updates as it gets closer to convergence. 3.4.2.2 Adaptive learning rate methods. Adaptive learning rate methods, such as AdaGrad, RMSProp, and ADAM, dynamically adjust the learning rate based on the gradients of the parameters. These methods adaptively scale the learning rate for each parameter, allowing for faster convergence and better performance on different types of data. They have become popular choices for optimizing neural networks due to their ability to handle sparse gradients and noisy data. 3.4.3 Network architecture design. The architecture of a neural network plays a crucial role in its performance. Here are some strategies to improve the architecture of feedforward neural networks. 3.4.3.1 Depth and width. Increasing the depth and width of a neural network can improve its representational power and ability to learn complex patterns. Deeper networks can capture hierarchical features, while wider networks can capture more diverse and fine-grained features. However, it is important to strike a balance between model complexity and overfitting. Adding too many layers or neurons can lead to increased computational costs and potential overfitting. 3.4.3.2 Batch normalization. Batch normalization is a technique that normalizes the activations of each layer in a neural network. It helps address the internal covariate shift problem, where the distribution of the inputs to each layer changes during training. By normalizing the inputs, batch normalization reduces the dependence of the network on the scale and distribution of the input data, making the training process more stable and efficient. It has been shown to improve the convergence speed and generalization ability of neural networks. 3.4.4 Early stopping. Early stopping is a simple yet effective technique to prevent overfitting in neural networks. It involves monitoring the validation loss during training and stopping the training process when the validation loss starts to increase. By stopping the training early, the model is prevented from overfitting to the training data and can achieve better generalization performance. 3.4.5 Data augmentation. Data augmentation is a technique used to artificially increase the size of the training dataset by applying various transformations to the existing data. By introducing variations such as rotations, translations, and flips, data augmentation helps the model generalize better to unseen data and reduces the risk of overfitting. This technique is particularly useful when the available training data is limited. In conclusion, improving the performance of feedforward neural networks involves a combination of regularization techniques, optimizing the learning rate, designing an appropriate network architecture, and employing strategies like early stopping and data augmentation. By carefully considering these factors and experimenting with different approaches, it is possible to enhance the capabilities of feedforward neural networks and achieve better results in various applications. 4. Recurrent neural networks. 4.1 Introduction to recurrent neural networks. Recurrent neural networks (RNNs) are a type of artificial neural network that are designed to process sequential data. Unlike feedforward neural networks, which only propagate information in one direction, from input to output, RNNs have connections that allow information to flow in loops, enabling them to retain and utilize information from previous steps in the sequence. The ability of RNNs to capture temporal dependencies makes them particularly well suited for tasks such as speech recognition, natural language processing, and time series analysis. By maintaining an internal memory, RNNs can effectively model and predict patterns in sequential data. 4.1.1 Architecture of recurrent neural networks. The architecture of a recurrent neural network consists of recurrent connections, which allow information to be passed from one step in the sequence to the next. At each step, the RNN takes an input and produces an output, while also updating its internal state. This internal state serves as a memory that retains information from previous steps, allowing the network to make predictions based on the context of the entire sequence. The most common type of RNN architecture is the long short-term memory (LSTM) network. LSTMs address the vanishing gradient problem that can occur in traditional RNNs, where the gradients become extremely small as they propagate back through time, making it difficult for the network to learn long-term dependencies. LSTMs use a gating mechanism that allows them to selectively retain or forget information from previous steps, enabling them to capture long-term dependencies more effectively. Another popular variant of RNNs is the gated recurrent unit (GRU). GRUs also address the vanishing gradient problem by using gating mechanisms, but with a simpler architecture compared to LSTMs. GRUs have been shown to perform well in various tasks and are computationally more efficient than LSTMs. 4.1.2 Training recurrent neural networks. Training recurrent neural networks involves optimizing the network's parameters to minimize a loss function. The most commonly used optimization algorithm for RNNs is backpropagation through time (BPTT), which is an extension of the backpropagation algorithm used in feedforward neural networks. BPTT works by unfolding the recurrent connections in the network over a fixed number of time steps, creating a computational graph that resembles a feedforward neural network. The gradients are then computed using this unfolded graph and used to update the network's parameters. However, training RNNs can be challenging due to the vanishing and exploding gradient problems. The vanishing gradient problem occurs when the gradients become extremely small, making it difficult for the network to learn long-term dependencies. On the other hand, the exploding gradient problem occurs when the gradients become extremely large, causing the network's parameters to update in large steps and destabilizing the learning process. To mitigate these issues, various techniques have been developed, such as gradient clipping, which limits the magnitude of the gradients, and weight initialization strategies, which help to stabilize the learning process. Additionally, using LSTM or GRU architectures can also alleviate the vanishing gradient problem to some extent. 4.1.3 Applications of recurrent neural networks. Recurrent neural networks have found numerous applications in various domains. One of the most prominent applications is natural language processing (NLP). RNNs can be used for tasks such as language modeling, machine translation, sentiment analysis, and text generation. By capturing the sequential nature of language, RNNs can generate coherent and contextually relevant text. In the field of speech recognition, RNNs have been used to model the temporal dependencies in audio signals, enabling accurate transcription and voice command recognition. RNNs have also been applied to time series analysis, where they can predict future values based on historical data, making them useful for tasks such as stock market prediction, weather forecasting, and anomaly detection. Furthermore, RNNs have been used in image and video analysis tasks. By treating images or video frames as sequential data, RNNs can capture the temporal dependencies and extract meaningful information. This has led to applications such as action recognition, video captioning, and video summarization. In summary, recurrent neural networks are a powerful class of neural networks that excel at processing sequential data. Their ability to capture temporal dependencies makes them well suited for a wide range of tasks, including natural language processing, speech recognition, time series analysis, and image-video analysis. With ongoing research and advancements, RNNs continue to play a crucial role in the development of intelligent systems. 4.2 Architecture of recurrent neural networks. Recurrent neural networks (RNNs) are a type of artificial neural network that are designed to process sequential data by utilizing feedback connections. Unlike feedforward neural networks, which only propagate information in one direction, from input to output, RNNs have connections that allow information to flow in loops, enabling them to retain and utilize information from previous time steps. This unique architecture makes RNNs particularly effective for tasks that involve sequential data, such as natural language processing, speech recognition, and time series analysis. 4.2.1 Structure of recurrent neural networks. The basic structure of a recurrent neural network consists of three main components: the input layer, the hidden layer, and the output layer. The input layer receives the sequential input data, which could be a sequence of words, audio samples, or any other form of sequential data. The hidden layer contains recurrent connections that allow the network to retain information from previous time steps. Finally, the output layer produces the desired output based on the information processed by the hidden layer. At each time step, the input data is fed into the network, and the hidden layer updates its internal state based on the current input and the previous hidden state. This allows the network to capture dependencies and patterns in the sequential data. The updated hidden state is then used to generate the output for that time step. The process is repeated for each time step in the sequence, allowing the network to process the entire sequence and generate a sequence of outputs. 4.2.2 Types of recurrent neural networks. There are several variations of recurrent neural networks, each with its own architectural modifications to address specific challenges. Some of the commonly used types of RNNs include 4.2.2.1 Elman RNN. The Elman RNN, also known as the simple RNN, is one of the earliest and simplest forms of recurrent neural networks. It has a single hidden layer that connects the input layer to itself, allowing the network to retain information from previous time steps. However, Elman RNNs suffer from the vanishing gradient problem, which limits their ability to capture long-term dependencies in the data. 4.2.2.2 Jordan RNN. The Jordan RNN is another type of recurrent neural network that has a feedback connection from the output layer to the hidden layer. This allows the network to utilize the output information from previous time steps when processing the current input. Jordan RNNs are particularly useful for tasks that require the network to generate output sequences that depend on previous outputs. 4.2.2.3 Long Short-Term Memory LSTM. LSTM is a type of recurrent neural network that addresses the vanishing gradient problem by introducing memory cells and gating mechanisms. The memory cells allow the network to retain information over long sequences, while the gating mechanisms control the flow of information within the network. This enables LSTMs to capture long-term dependencies and process sequential data more effectively. 4.2.2.4 Gated Recurrent Unit GRU. Similar to LSTM, the Gated Recurrent Unit GRU is designed to address the vanishing gradient problem and capture long-term dependencies. GRUs have a simplified architecture compared to LSTMs, with fewer gating mechanisms. This makes them computationally more efficient while still maintaining good performance on sequential tasks. 4.2.3 Training Recurrent Neural Networks. Training recurrent neural networks involves optimizing the network's parameters to minimize the difference between the predicted output and the true output. This is typically done using the backpropagation through time (BPTT) algorithm, which is an extension of the backpropagation algorithm used in feedforward neural networks. In BPTT, the network's parameters are updated by propagating the error gradient back through time, from the output layer to the input layer. This allows the network to learn the dependencies between the input and output sequences. However, training RNNs can be challenging due to the vanishing gradient problem, where the gradients become extremely small as they propagate back through time. This can result in slow convergence or the network failing to capture long-term dependencies. To address the vanishing gradient problem, techniques such as gradient clipping, weight initialization, and using activation functions like ReLU or LSTM are commonly employed. Additionally, advanced optimization algorithms like ADAM or RMS-prop can be used to improve the training process. 4.2.4 Applications of recurrent neural networks. Recurrent neural networks have found numerous applications in various domains due to their ability to process sequential data effectively. Some of the notable applications include 4.2.4.1 Natural language processing. RNNs have been widely used in natural language processing tasks such as language modeling, machine translation, sentiment analysis, and text generation. Their ability to capture the contextual information in text makes them well suited for these tasks. 4.2.4.2 Speech recognition. RNNs have been successfully applied to speech recognition tasks, where they can process audio sequences and convert them into text. By modeling the temporal dependencies in speech data, RNNs can improve the accuracy of speech recognition systems. 4.2.4.3 Time series analysis. RNNs are commonly used for time series analysis tasks such as stock market prediction, weather forecasting, and anomaly detection. By considering the temporal dependencies in the data, RNNs can capture patterns and make accurate predictions. 4.2.4.4 Music generation. RNNs have been used to generate music by learning patterns from existing musical compositions. By modeling the sequential nature of music, RNNs can generate new melodies and harmonies that resemble the training data. In conclusion, recurrent neural networks are a powerful type of artificial neural network that can effectively process sequential data. Their unique architecture allows them to capture dependencies and patterns in the data, making them well suited for tasks such as natural language processing, speech recognition, and time series analysis. With advancements in training techniques and optimization algorithms, RNNs continue to be at the forefront of research and application in the field of neural networks. 4.3 Training recurrent neural networks. Training recurrent neural networks, RNNs, is a crucial step in harnessing their power to solve complex problems. Unlike feedforward neural networks, which process data in a sequential manner, RNNs have the ability to capture temporal dependencies and handle sequential data effectively. In this section, we will explore the training process of RNNs, including the challenges involved and the techniques used to overcome them. 4.3.1 Backpropagation through time. The most common method used to train RNNs is called backpropagation through time, BPTT. BPTT is an extension of the backpropagation algorithm used in feedforward neural networks. It allows the gradients to flow through the recurrent connections over a sequence of time steps. In BPTT, the RNN is unrolled through time, creating a series of interconnected feedforward neural networks. Each time step is treated as a separate layer, and the gradients are computed using the chain rule. The gradients are then propagated backward through time, updating the weights and biases of the RNN. However, BPTT has a limitation known as the vanishing gradient problem. This problem arises when the gradients diminish exponentially as they propagate backward through time, making it difficult for the RNN to learn long-term dependencies. To address this issue, various techniques have been developed, such as gradient clipping and using activation functions that alleviate the vanishing gradient problem, like the rectified linear unit ReLU or the long short-term memory LSTM cell. 4.3.2 Long short-term memory LSTM. LSTM is a type of RNN architecture that has been specifically designed to address the vanishing gradient problem. It introduces a memory cell that allows the network to retain information over long sequences. The LSTM cell consists of three main components: the input gate, the forget gate, and the output gate. The input gate determines how much new information should be stored in the memory cell. It takes into account the current input and the previous hidden state. The forget gate controls the amount of information that should be discarded from the memory cell. It considers the current input and the previous hidden state as well. Finally, the output gate determines how much information from the memory cell should be passed to the next hidden state in the output. By using these gates, the LSTM cell can selectively retain or discard information, allowing it to capture long-term dependencies more effectively. The gradients can flow through the memory cell without being diminished, enabling the network to learn from long sequences of data. 4.3.3 Training strategies for RNNs. Training RNNs can be challenging due to the nature of sequential data and the long-term dependencies they need to capture. Here are some strategies commonly used to improve the training process. 4.3.3.1 Truncated backpropagation through time, TBPTT. TBPTT is a variation of BPTT that addresses the computational complexity of training RNNs on long sequences. Instead of propagating the gradients through the entire sequence, TBPTT breaks the sequence into smaller segments or chunks. The gradients are computed and updated within each chunk, and the hidden state is carried over to the next chunk. This approach reduces the memory requirements and allows for more efficient training. 4.3.3.2 Teacher forcing. Teacher forcing is a technique used during training to improve the convergence of RNNs. Instead of using the predicted output at each time step as the input for the next time step, the ground truth output is fed as input. This helps to stabilize the training process and reduce the impact of errors made during prediction. However, it can lead to a discrepancy between training and inference, as the model becomes reliant on the ground truth input. 4.3.3.3 Regularization techniques. Regularization techniques, such as dropout and weight decay, can also be applied to RNNs to prevent overfitting and improve generalization. Dropout randomly sets a fraction of the hidden units to zero during training, forcing the network to learn more robust representations. Weight decay adds a penalty term to the loss function, discouraging large weights and promoting simpler models. 4.3.4 Challenges in future directions. Training RNNs still poses several challenges, despite the advancements made in recent years. One major challenge is the difficulty of training deep RNN architectures. As the depth of the network increases, the gradients can become unstable, leading to training difficulties. Techniques like residual connections and skip connections have been proposed to address this issue. Another challenge is the efficient training of RNNs on large-scale datasets. The computational requirements can be overwhelming, especially when dealing with long sequences or high-dimensional data. Researchers are exploring techniques such as parallel computing and distributed training to overcome these challenges. In the future, we can expect further advancements in training algorithms and architectures for RNNs. The development of more efficient optimization algorithms, such as adaptive learning rate methods, can help improve the convergence speed and stability of RNN training. Additionally, the exploration of novel architectures, such as attention mechanisms and transformer models, can enhance the ability of RNNs to capture complex dependencies in sequential data. Training recurrent neural networks is a complex task that requires careful consideration of the architecture, optimization algorithms, and training strategies. By understanding the challenges involved and utilizing the appropriate techniques, we can unlock the full potential of RNNs and leverage their power in various applications, including natural language processing, speech recognition, and time series analysis. 4.4 Applications of recurrent neural networks. Recurrent neural networks, RNNs, have gained significant attention in recent years due to their ability to process sequential data and capture temporal dependencies. This unique characteristic makes them well suited for a wide range of applications across various domains. In this section, we will explore some of the key applications of recurrent neural networks and how they have revolutionized these fields. 4.4.1 Natural language processing. One of the most prominent applications of recurrent neural networks is in the field of natural language processing, NLP. RNNs have proven to be highly effective in tasks such as language modeling, machine translation, sentiment analysis, and text generation. The ability of RNNs to model the sequential nature of language allows them to capture the context and dependencies between words, making them ideal for tasks that involve understanding and generating human language. For example, in machine translation, RNNs can be used to build powerful models that can translate text from one language to another. By processing the input sentence word by word, the RNN can generate the corresponding translated sentence, taking into account the context and grammar of the target language. Similarly, in sentiment analysis, RNNs can analyze the sentiment of a given text by considering the sequence of words and their relationships. 4.4.2 Speech recognition. Another important application of recurrent neural networks is in the field of speech recognition. RNNs have been widely used to build speech recognition systems that can convert spoken language into written text. By modeling the temporal dependencies in speech signals, RNNs can effectively capture the phonetic and linguistic patterns present in the audio data. In speech recognition, RNNs are typically used in conjunction with other techniques such as hidden Markov models, HMMs, to build robust and accurate systems. The RNN component is responsible for modeling the acoustic features of the speech signal, while the HEM component handles the language modeling and decoding. This combination of RNNs and HMMs has led to significant advancements in speech recognition technology, enabling applications such as voice assistants, transcription services, and voice-controlled systems. 4.4.3 Time series analysis. Recurrent neural networks have also found extensive applications in time series analysis. Time series data is characterized by its sequential nature, where each data point is dependent on the previous ones. RNNs can effectively capture these dependencies and make accurate predictions based on the historical data. In finance, RNNs have been used for stock market prediction, where the network learns from historical stock prices and other relevant factors to forecast future prices. Similarly, in weather forecasting, RNNs can analyze historical weather data to predict future weather conditions. RNNs have also been applied to other domains such as energy load forecasting, sales forecasting, and anomaly detection in time series data. 4.4.4 Music generation. Recurrent neural networks have shown remarkable capabilities in generating music. By training on a large dataset of musical compositions, RNNs can learn the patterns and structures present in music and generate new compositions that resemble the training data. This has opened up exciting possibilities in the field of music composition and generation. Music generation using RNNs involves training the network on a sequence of musical notes or chords and then using the trained model to generate new sequences. The generated music can be in various styles and genres, depending on the training data. This application has been used by musicians, composers, and music enthusiasts to explore new musical ideas, create background music for videos, and even assist in the creative process of composing music. 4.4.5 Video analysis. RNNs have also been applied to video analysis tasks such as action recognition, video captioning, and video prediction. By processing the sequential frames of a video, RNNs can understand the temporal dynamics and extract meaningful information from the visual data. In action recognition, RNNs can classify different actions performed in a video, such as walking, running, or jumping. Video captioning involves generating textual descriptions of the content in a video, where RNNs can generate captions that accurately describe the events and objects in the video. Video prediction, on the other hand, aims to predict future frames in a video sequence, which has applications in video compression, video synthesis, and video editing. These are just a few examples of the wide range of applications of recurrent neural networks. From natural language processing to speech recognition, time series analysis, music generation, and video analysis, RNNs have revolutionized these fields by providing powerful tools to model and understand sequential data. As research in this area continues to advance, we can expect even more innovative applications of RNNs in the future. 5. Convolutional neural networks. 5.1 Introduction to convolutional neural networks. Convolutional neural networks, CNNs, are a type of artificial neural network that have revolutionized the field of computer vision and image processing. CNNs are specifically designed to process data with a grid-like structure, such as images, and have been incredibly successful in tasks such as image classification, object detection, and image segmentation. 5.1.1 Structure and function of convolutional neural networks. At their core, CNNs are composed of multiple layers that work together to extract meaningful features from input data. The key components of a CNN include convolutional layers, pooling layers, and fully connected layers. Convolutional layers are responsible for learning and detecting local patterns in the input data. They consist of a set of learnable filters, also known as kernels, which are convolved with the input data to produce feature maps. Each filter learns to detect a specific feature, such as edges, corners, or textures, by sliding across the input data and performing element-wise multiplications and summations. Pooling layers, on the other hand, are used to reduce the spatial dimensions of the feature maps while retaining the most important information. The most common pooling operation is max pooling, which selects the maximum value within a small window and discards the rest. This downsampling process helps to make the network more robust to variations in the input data and reduces the computational complexity. Fully connected layers, also known as dense layers, are responsible for making the final predictions based on the extracted features. These layers connect every neuron in the previous layer to every neuron in the current layer, allowing for complex relationships to be learned. The output of the fully connected layers is typically fed into a softmax activation function to produce the final probability distribution over the different classes in a classification task. 5.1.2 Architecture of convolutional neural networks. The architecture of a CNN refers to the specific arrangement and connectivity of its layers. CNN architectures can vary in depth, width, and the number of parameters. Some popular CNN architectures include LeNet-5, AlexNet, VGGNet, GoogleNet, and ResNet. LeNet-5, proposed by Yann LeCun in 1998, was one of the first successful CNN architectures. It consists of two convolutional layers followed by two fully connected layers. LeNet-5 was primarily designed for handwritten digit recognition and laid the foundation for future advancements in CNNs. AlexNet, introduced by Alex Krzyzewski et al. In 2012, was a breakthrough architecture that significantly improved the performance of CNNs. It consisted of 5 convolutional layers, followed by 3 fully connected layers. AlexNet achieved state-of-the-art results on the ImageNet dataset and demonstrated the power of deep CNNs. VGGNet, proposed by Karen Simonyan and Andrew Zisserman in 2014, is known for its simplicity and depth. It consists of 16 or 19 layers with small 3x3 filters and achieved excellent performance on various image classification tasks. VGGNet demonstrated that increasing the depth of CNNs can lead to better performance. GoogleNet, introduced by Christian Szegedy et al. In 2014, introduced the concept of inception modules that allowed for efficient use of computational resources. GoogleNet achieved state-of-the-art performance on the ImageNet dataset while being computationally efficient. ResNet, proposed by Kaminghi et al. In 2015, addressed the problem of vanishing gradients in deep CNNs. It introduced the concept of residual connections, where the output of a previous layer is added to the output of the current layer. ResNet architectures with hundreds of layers have been successfully trained and achieved outstanding performance on various tasks. 5.1.3 Training convolutional neural networks. Training a CNN involves 2 main steps: forward propagation and backpropagation. During forward propagation, the input data is passed through the network, and the output is computed. The computed output is then compared to the ground truth labels using a loss function, such as cross-entropy loss. Backpropagation is used to update the network's parameters based on the computed loss. It involves computing the gradients of the loss with respect to the network's parameters using the chain rule. These gradients are then used to update the parameters using an optimization algorithm, such as stochastic gradient descent (SGD) or its variants. To prevent overfitting, regularization techniques such as dropout and weight decay are commonly used. Dropout randomly sets a fraction of the neurons to 0 during training, which helps to prevent the network from relying too heavily on specific neurons. Weight decay adds a penalty term to the loss function to encourage smaller weights, which helps to prevent the network from overfitting the training data. 5.1.4 Applications of convolutional neural networks. Convolutional neural networks have found applications in various domains, with computer vision being the most prominent one. They have been successfully used for image classification, where the task is to assign a label to an input image from a predefined set of classes. CNNs have achieved human-level performance on challenging datasets such as ImageNet. Object detection is another important application of CNNs, where the goal is to localize and classify objects within an image. CNN-based object detection algorithms, such as faster RCNN and YOLO, have achieved remarkable accuracy and real-time performance. CNNs have also been used for image segmentation, which involves assigning a label to each pixel in an image. This task is crucial in medical imaging, where CNNs have been used for tasks such as tumor segmentation and disease diagnosis. Furthermore, CNNs have been applied to tasks such as facial recognition, scene understanding, video analysis, and even natural language processing. Their ability to automatically learn hierarchical representations from raw data makes them a powerful tool in various domains. In conclusion, convolutional neural networks have revolutionized the field of computer vision and image processing. Their ability to automatically learn and extract meaningful features from input data has led to significant advancements in tasks such as image classification, object detection, and image segmentation. With the continuous development of CNN architectures and training techniques, we can expect even more exciting applications and breakthroughs in the future. 5.2 Architecture of Convolutional Neural Networks. Convolutional neural networks, CNNs, are a specialized type of artificial neural network that have revolutionized the field of computer vision. They are designed to process data with a grid-like structure, such as images, and have proven to be highly effective in tasks such as image classification, object detection, and image segmentation. In this section, we will explore the architecture of CNNs and understand how they are able to extract meaningful features from images. 5.2.1 Convolutional Layers. The key building block of a CNN is the convolutional layer. This layer applies a set of learnable filters, also known as kernels or feature detectors, to the input image. Each filter is a small matrix of weights that is convolved with the input image, resulting in a feature map. The purpose of these filters is to detect different patterns or features in the image, such as edges, corners, or textures. During the convolution operation, the filter slides over the input image, computing the dot product between the filter weights and the corresponding pixels in the image. This process is repeated for every position in the image, producing a feature map that highlights the presence of certain features. The size of the feature map depends on the size of the input image, the size of the filter, and the stride, which determines the amount of movement of the filter at each step. One important characteristic of convolutional layers is their ability to capture local spatial dependencies. By sharing weights across different regions of the input image, CNNs are able to detect the same features regardless of their location. This property makes CNNs translation invariant, meaning they can recognize patterns regardless of their position in the image. 5.2.2 Pooling layers. Pooling layers are often used in conjunction with convolutional layers to reduce the spatial dimensions of the feature maps. The most common type of pooling is max pooling, which divides the input image into non-overlapping regions and outputs the maximum value within each region. This operation effectively reduces the size of the feature maps while preserving the most important information. Pooling layers serve two main purposes in CNNs. First, they help to make the network more robust to small variations in the input image, such as translations or distortions. By selecting the maximum value within each region, pooling layers capture the most salient features while discarding irrelevant details. Second, pooling layers reduce the computational complexity of the network by reducing the number of parameters and the size of the feature maps. 5.2.3 Fully Connected Layers. After several convolutional and pooling layers, the output is typically flattened into a one-dimensional vector and fed into one or more fully connected layers. These layers are similar to the ones found in traditional artificial neural networks, where each neuron is connected to every neuron in the previous layer. Fully connected layers are responsible for learning high-level representations of the input data and making predictions based on these representations. The number of neurons in the fully connected layers is typically much larger than the number of neurons in the convolutional layers. This allows the network to learn complex relationships between the extracted features and the target output. The final layer of the network is usually a softmax layer, which produces a probability distribution over the different classes in a classification task. 5.2.4 Activation Functions. Activation functions play a crucial role in CNNs by introducing nonlinearities into the network. They are applied element-wise to the output of each neuron and determine whether it should be activated or not. The most commonly used activation function in CNNs is the rectified linear unit, ReLU, which sets all negative values to 0 and keeps positive values unchanged. ReLU has been shown to be effective in preventing the vanishing gradient problem and accelerating the convergence of the network. Other popular activation functions include the sigmoid function and the hyperbolic tangent function. The sigmoid function squashes the output of each neuron between 0 and 1, making it suitable for binary classification tasks. The hyperbolic tangent function, on the other hand, squashes the output between -1 and 1, allowing the network to learn both positive and negative relationships. 5.2.5 Skip connections. Skip connections, also known as residual connections, are a recent innovation in CNN architecture that have greatly improved the performance of deep networks. They involve connecting the output of one layer to the input of a later layer, effectively creating shortcuts in the network. This allows the network to learn both low-level and high-level features simultaneously, leading to better feature representation and easier optimization. Skip connections are particularly useful in very deep networks, where the gradient can easily vanish or explode during backpropagation. By providing a direct path for the gradient to flow, skip connections help to alleviate these issues and enable the network to learn more effectively. One popular architecture that incorporates skip connections is the ResNet, which has achieved state-of-the-art performance in various computer vision tasks. In conclusion, the architecture of convolutional neural networks is specifically designed to process grid-like data, such as images. By using convolutional layers to extract features, pooling layers to reduce spatial dimensions, and fully connected layers to learn high-level representations, CNNs are able to achieve remarkable performance in computer vision tasks. Activation functions introduce nonlinearities, while skip connections enable the network to learn more effectively in deep architectures. The combination of these architectural elements has led to significant advancements in the field of computer vision and has paved the way for many practical applications of CNNs. 5.3 Training convolutional neural networks. Training convolutional neural networks (CNNs) is a crucial step in harnessing their power to solve complex problems in various domains such as computer vision, natural language processing, and speech recognition. In this section, we will explore the process of training CNNs, including data preparation, model architecture, optimization techniques, and evaluation. 5.3.1 Data preparation. Before training a CNN, it is essential to prepare the data appropriately. This involves collecting and preprocessing the data to ensure it is in a suitable format for the network to learn from. In computer vision tasks, such as image classification or object detection, the data usually consists of a large number of images. The first step in data preparation is to divide the dataset into training, validation, and testing sets. The training set is used to train the CNN, the validation set is used to tune the hyperparameters and monitor the model's performance during training, and the testing set is used to evaluate the final performance of the trained model. Next, the images in the dataset need to be preprocessed. This typically involves resizing the images to a fixed size, normalizing the pixel values, and applying data augmentation techniques such as random rotations, translations, and flips. Data augmentation helps to increase the diversity of the training data and improve the generalization ability of the CNN. 5.3.2 Model architecture. The architecture of a CNN plays a crucial role in its ability to learn and generalize from the data. CNNs consist of multiple layers, including convolutional layers, pooling layers, and fully connected layers. Convolutional layers are the core building blocks of CNNs. They apply a set of learnable filters to the input data, extracting local features and capturing spatial relationships. The output of a convolutional layer is called a feature map. Pooling layers are used to reduce the spatial dimensions of the feature maps while retaining the most important information. Common pooling operations include max pooling and average pooling. Fully connected layers are responsible for making the final predictions based on the extracted features. They take the flattened feature maps as input and apply a set of learnable weights to produce the output. The architecture of a CNN can vary depending on the specific task and dataset. It is often designed through a process of trial and error, experimenting with different layer configurations, filter sizes, and depths. Techniques such as transfer learning, discussed in Chapter 8, can also be used to leverage pre-trained CNN models and adapt them to new tasks. 5.3.3 Optimization techniques. Training a CNN involves optimizing the model's parameters to minimize a loss function. This is typically done using an optimization algorithm such as stochastic gradient descent, SGD, or its variants. During training, the CNN is presented with batches of training samples, and the gradients of the loss function with respect to the model parameters are computed. The optimizer then updates the parameters in the direction that minimizes the loss. To improve the convergence and generalization of the CNN, several optimization techniques can be employed. One common technique is weight regularization, which adds a penalty term to the loss function to discourage large weights. This helps prevent overfitting and improves the model's ability to generalize to unseen data. Another technique is learning rate scheduling, where the learning rate is adjusted during training. Initially, a higher learning rate is used to make larger updates to the parameters, and as training progresses, the learning rate is reduced to make smaller, more precise updates. This helps the optimizer to converge to a better solution. 5.3.4 Evaluation. Once the CNN is trained, it is crucial to evaluate its performance on unseen data. This is typically done using the testing set that was set aside during the data preparation phase. Evaluation metrics such as accuracy, precision, recall, and F1 score can be used to assess the performance of the CNN. These metrics provide insights into the model's ability to correctly classify or detect objects in the testing data. It is also important to analyze the model's performance on different classes or categories within the dataset. This can help identify any biases or imbalances in the model's predictions and guide further improvements. In addition to quantitative evaluation metrics, qualitative analysis can also be performed by visually inspecting the CNN's predictions. This can help identify cases where the model fails or makes incorrect predictions, providing insights into potential areas for improvement. In conclusion, training convolutional neural networks involves careful data preparation, designing an appropriate model architecture, optimizing the model's parameters, and evaluating its performance. By following these steps and leveraging the power of CNNs, we can tackle complex problems in computer vision and other domains, opening up new possibilities for innovation and advancement. 5.4 Applications of convolutional neural networks. Convolutional neural networks, CNNs, have revolutionized the field of computer vision and have become the go-to model for various image and video-related tasks. Their ability to automatically learn and extract features from raw data has made them incredibly powerful in a wide range of applications. In this section, we will explore some of the most common and impactful applications of convolutional neural networks. 5.4.1 Image classification. One of the most well-known applications of CNNs is image classification. Given an input image, the task is to assign it to one of several predefined categories. CNNs excel at this task by learning hierarchical representations of images. They can automatically learn to detect low-level features such as edges and textures, and then combine them to recognize higher-level features like shapes and objects. This hierarchical approach allows CNNs to achieve state-of-the-art performance on image classification benchmarks, surpassing human-level accuracy in some cases. Image classification has numerous practical applications. For example, it can be used in autonomous vehicles to identify and classify objects on the road, such as pedestrians, traffic signs, and vehicles. It is also used in medical imaging to assist doctors in diagnosing diseases by analyzing medical scans. Additionally, image classification is used in security systems for facial recognition and in e-commerce for product categorization. 5.4.2 Object detection. Object detection is another important application of CNNs. Unlike image classification, object detection aims to not only classify objects in an image but also locate their positions. CNNs can be trained to output bounding boxes around objects of interest, along with their corresponding class labels. This allows for more detailed analysis of images and enables applications such as object tracking, surveillance, and augmented reality. Object detection has a wide range of practical applications. In the field of autonomous driving, CNN-based object detection systems are used to detect and track pedestrians, vehicles, and other obstacles on the road. In the retail industry, object detection is used for inventory management and shelf monitoring. It can also be used in security systems to detect and track suspicious activities in real time. 5.4.3 Image segmentation. Image segmentation is the task of dividing an image into meaningful regions or segments. Unlike object detection, which focuses on identifying and localizing specific objects, image segmentation aims to assign a label to each pixel in the image, indicating which segment it belongs to. CNNs have been highly successful in image segmentation tasks due to their ability to capture spatial dependencies and learn complex patterns. Image segmentation has numerous applications in various domains. In medical imaging, it is used for tumor detection and delineation, organ segmentation, and disease diagnosis. In the field of autonomous robotics, image segmentation is used for scene understanding and object manipulation. It is also used in satellite imagery analysis for land cover classification and urban planning. 5.4.4 Image generation. CNNs can also be used for image generation tasks, where the goal is to generate new images that resemble a given set of training examples. This is achieved by training a CNN to learn the underlying distribution of the training data and then sampling from this learned distribution to generate new images. This application of CNNs has gained significant attention in recent years, leading to the development of generative adversarial networks (GANs) and variational autoencoders (VAEs). Image generation has various applications, including data augmentation for training other models, creating realistic synthetic images for computer graphics and virtual reality, and generating artistic images for creative purposes. It also has potential applications in the medical field, such as generating synthetic medical images for training and testing medical imaging algorithms. 5.4.5 Video analysis. CNNs can be extended to analyze videos by processing each frame individually and then incorporating temporal information across frames. This allows for tasks such as action recognition, video captioning, and video object tracking. By leveraging the hierarchical representations learned by CNNs, video analysis models can capture both spatial and temporal dependencies, enabling them to understand and interpret complex video data. Video analysis has numerous applications, including surveillance and security systems, where it can be used for activity recognition and anomaly detection. It is also used in the entertainment industry for video editing and special effects. Additionally, video analysis has applications in healthcare for monitoring patient movements and analyzing surgical procedures. In conclusion, convolutional neural networks have revolutionized the field of computer vision and have found applications in various domains. From image classification and object detection to image segmentation and video analysis, CNNs have demonstrated their effectiveness in solving complex visual tasks. As the field continues to advance, we can expect to see even more innovative applications of CNNs in the future. 6. Generative adversarial networks. 6.1 Introduction to generative adversarial networks. Generative adversarial networks (GANs) are a type of artificial neural network that have gained significant attention and popularity in recent years. GANs are a powerful framework for generating new data that resembles a given training dataset. They have revolutionized the field of generative modeling and have found applications in various domains, including image synthesis, text generation, and music composition. 6.1.1 What are generative adversarial networks? At the core of a GAN are two neural networks, the generator and the discriminator. The generator network takes random noise as input and generates synthetic data samples. The discriminator network, on the other hand, tries to distinguish between the real data samples from the training dataset and the synthetic samples generated by the generator. The two networks are trained simultaneously in a competitive manner, where the generator aims to produce realistic samples that can fool the discriminator, while the discriminator aims to correctly classify the real and synthetic samples. The training process of a GAN can be thought of as a game between the generator and the discriminator. As the training progresses, the generator learns to produce increasingly realistic samples, while the discriminator becomes more adept at distinguishing between real and synthetic data. This adversarial training process leads to the development of a generator network that can produce high-quality synthetic data that closely resembles the real data distribution. 6.1.2 Architecture of generative adversarial networks. The architecture of a GAN consists of two main components, the generator and the discriminator. The generator network typically consists of multiple layers of neural units, such as fully connected layers or convolutional layers, that transform the random noise input into a synthetic data sample. The discriminator network, on the other hand, also consists of multiple layers that process the input data and output a probability score indicating the likelihood of the input being real or synthetic. The generator and discriminator networks are trained using a loss function that captures the adversarial nature of the training process. The generator aims to minimize this loss function, while the discriminator aims to maximize it. This adversarial objective function drives the generator to produce samples that are increasingly difficult for the discriminator to distinguish from real data. 6.1.3 Training generative adversarial networks. Training a GAN involves an iterative process where the generator and discriminator networks are updated alternately. In each iteration, a batch of real data samples is randomly selected from the training dataset, and a batch of random noise vectors is generated as input for the generator. The generator then generates synthetic samples, which are combined with the real samples to form a training batch. The discriminator is trained on this batch by minimizing a binary cross-entropy loss function, which measures the difference between the predicted probabilities and the true labels, real or synthetic. The generator is trained by maximizing the same loss function, but with the labels flipped. This adversarial training process continues for multiple iterations, allowing the generator to learn to produce increasingly realistic samples. 6.1.4 Applications of generative adversarial networks. Generative adversarial networks have found numerous applications in various domains. One of the most well-known applications is in image synthesis, where GANs can generate realistic images that resemble a given training dataset. This has been used for tasks such as generating new artwork, creating realistic avatars, and even generating high-resolution images from low-resolution inputs. GANs have also been applied to text generation tasks, such as generating realistic and coherent sentences or even entire articles. This has implications in natural language processing, where GANs can be used to generate text for chatbots, language translation, and content generation. In addition to image and text generation, GANs have been used in music composition, where they can generate new melodies or even entire musical compositions. This has opened up new possibilities in the field of music production and has allowed musicians to explore new creative avenues. Furthermore, GANs have been used in data augmentation, where synthetic data samples are generated to supplement a limited training dataset. This can improve the performance of machine learning models by providing more diverse and representative training data. Overall, generative adversarial networks have revolutionized the field of generative modeling and have enabled the generation of realistic and high-quality synthetic data. Their applications span across various domains and continue to expand as researchers explore new possibilities and advancements in the field. 6.2 Architecture of generative adversarial networks. Generative adversarial networks (GANs) are a type of artificial neural network that have gained significant attention in recent years due to their ability to generate realistic and high-quality synthetic data. GANs consist of two main components, a generator network and a discriminator network. These two networks work together in a competitive manner, where the generator tries to produce realistic data samples, and the discriminator tries to distinguish between real and fake samples. 6.2.1 Generator network. The generator network in a GAN is responsible for creating synthetic data samples that resemble the real data. It takes random noise as input and transforms it into a meaningful output that resembles the training data. The generator network typically consists of multiple layers of neurons, with each layer performing a specific transformation on the input data. The input to the generator network is usually a random vector or noise, which serves as a source of randomness for generating diverse samples. This noise vector is passed through a series of hidden layers, where each layer applies a nonlinear transformation to the input. The final layer of the generator network produces the synthetic data samples, which are then fed to the discriminator network for evaluation. The architecture of the generator network can vary depending on the specific application and the complexity of the data being generated. It can range from simple fully connected layers to more complex architectures such as convolutional or recurrent neural networks. The choice of architecture depends on the nature of the data and the desired output. 6.2.2 Discriminator network. The discriminator network in a GAN is responsible for distinguishing between real and fake data samples. It takes both real and synthetic data samples as input and outputs a probability score indicating the likelihood of the input being real or fake. The discriminator network is trained to improve its ability to correctly classify the samples over time. Similar to the generator network, the discriminator network also consists of multiple layers of neurons. It takes the input data and passes it through a series of hidden layers, where each layer applies a nonlinear transformation to the input. The final layer of the discriminator network produces a probability score, which is used to determine the authenticity of the input sample. The architecture of the discriminator network is typically designed to be more complex than the generator network. This is because the discriminator needs to be able to accurately distinguish between real and fake samples, which requires a higher level of discrimination power. Convolutional neural networks are commonly used as the architecture for the discriminator network, as they are well suited for image classification tasks. 6.2.3 Training process. The training process of a GAN involves a competitive game between the generator and the discriminator networks. The generator network tries to produce synthetic samples that are indistinguishable from the real data, while the discriminator network tries to correctly classify the samples as real or fake. During the training process, the generator and discriminator networks are trained alternately. In each training iteration, a batch of real data samples is randomly selected from the training dataset, and a batch of synthetic samples is generated by the generator network. These samples are then used to update the parameters of the discriminator network. The objective of the discriminator network is to maximize the probability of correctly classifying the real and fake samples. On the other hand, the objective of the generator network is to minimize the probability of the discriminator correctly classifying the fake samples. This adversarial training process creates a feedback loop, where the generator network learns to produce more realistic samples as the discriminator network becomes more accurate in distinguishing between real and fake samples. 6.2.4 Architectural Variations. While the basic architecture of GANs consists of a generator and a discriminator network, there have been several architectural variations proposed to improve the performance and stability of GANs. Some of these variations include conditional GANs. These GANs introduce additional information, such as class labels, as input to both the generator and discriminator networks. This allows for the generation of specific types of data samples based on the given conditions. Deep convolutional GANs (DCGANs). DCGANs use convolutional neural networks as the architecture for both the generator and discriminator networks. This allows for the generation of high-quality images and improves the stability of the training process. Wasserstein GANs (WGANs). WGANs introduce a new loss function based on the Wasserstein distance, which provides a more stable training process and better convergence properties compared to traditional GANs. Progressive GANs. Progressive GANs start with a low-resolution generator network and gradually increase the resolution as the training progresses. This allows for the generation of high-resolution images while maintaining stability during training. These architectural variations have contributed to the advancement of GANs and have enabled the generation of realistic and diverse synthetic data in various domains, including image synthesis, text generation, and music composition. In the next section, we will explore the training process of generative adversarial networks in more detail. 6.3 Training generative adversarial networks. Training generative adversarial networks (GANs) is a complex and challenging task that requires careful consideration of various factors. GANs are a type of artificial neural network that consists of two components, a generator and a discriminator. The generator is responsible for creating new data samples, while the discriminator's role is to distinguish between real and generated data. The training process involves a competitive game between these two components, where they continuously learn from each other's feedback. 6.3.1 The adversarial training process. The training process of GANs can be described as an adversarial game between the generator and the discriminator. Initially, both components are randomly initialized, and the generator produces synthetic data samples. The discriminator then evaluates these samples and provides feedback to the generator. The goal of the generator is to produce data that is indistinguishable from real data, while the discriminator aims to correctly classify the real and generated samples. During each training iteration, the generator and discriminator are updated alternately. The generator tries to improve its performance by generating more realistic samples that can fool the discriminator. On the other hand, the discriminator learns to become more accurate in distinguishing between real and generated data. This iterative process continues until both components reach a state of equilibrium, where the generator produces highly realistic samples, and the discriminator struggles to differentiate between real and generated data. 6.3.2 Loss functions in GANs. To train GANs effectively, appropriate loss functions are crucial. The generator and discriminator use different loss functions to optimize their performance. The generator's loss function aims to maximize the probability of the discriminator misclassifying the generated samples as real. On the other hand, the discriminator's loss function aims to correctly classify the real and generated samples. One commonly used loss function for GANs is the binary cross-entropy loss. The generator's loss is calculated based on the discriminator's output when evaluating the generated samples. The goal is to minimize this loss, indicating that the generator is producing samples that the discriminator cannot distinguish from real data. Conversely, the discriminator's loss is calculated based on its ability to correctly classify the real and generated samples. The discriminator aims to minimize this loss, indicating that it can accurately distinguish between the two types of data. 6.3.3 Training challenges and techniques. Training GANs can be challenging due to several factors. One common issue is the problem of mode collapse, where the generator produces a limited variety of samples, failing to capture the full diversity of the real data distribution. Another challenge is the instability of the training process, where the generator and discriminator can become stuck in a suboptimal equilibrium. To address these challenges, researchers have proposed various techniques. One approach is to use different architectures for the generator and discriminator, such as deep convolutional networks, to capture complex patterns in the data. Additionally, regularization techniques, such as weight decay and dropout, can be applied to prevent overfitting and improve the generalization ability of the models. Another technique is to use mini-batch discrimination, where the discriminator evaluates multiple samples at once, allowing it to consider the diversity of the generated samples. This helps to mitigate the mode collapse problem and encourages the generator to produce a wider range of samples. 6.3.4 Evaluation and Fine-Tuning. Evaluating the performance of GANs is a challenging task. Traditional evaluation metrics, such as accuracy or mean squared error, are not suitable for GANs because they focus on the quality of individual samples rather than the overall distribution. Instead, researchers have proposed alternative evaluation methods, such as the inception score and FRA copyright ched inception distance, which measure the diversity and quality of the generated samples. Once a GAN model is trained, fine-tuning can be performed to further improve its performance. Fine-tuning involves adjusting the model's parameters using additional data or by continuing the training process with a smaller learning rate. This process helps to refine the model and enhance its ability to generate high-quality samples. In conclusion, training generative adversarial networks is a complex and iterative process that involves a competitive game between the generator and discriminator. The choice of appropriate loss functions, along with various training techniques, is crucial for achieving optimal performance. Despite the challenges, GANs have shown remarkable success in generating realistic and diverse data, opening up exciting possibilities in fields such as image synthesis, text generation, and data augmentation. 6.4 Applications of generative adversarial networks. Generative adversarial networks (GANs) have gained significant attention in recent years due to their ability to generate realistic and high-quality data. GANs consist of two neural networks, a generator and a discriminator, which work together in a competitive manner. The generator network learns to generate synthetic data that resembles the real data, while the discriminator network learns to distinguish between real and fake data. This adversarial training process leads to the improvement of both networks over time. The applications of GANs are diverse and span across various domains. In this section, we will explore some of the most notable applications of GANs and how they have revolutionized different industries. 6.4.1 Image Generation and Synthesis. One of the most well-known applications of GANs is in image generation and synthesis. GANs have the ability to generate realistic images that are indistinguishable from real photographs. This has opened up new possibilities in the fields of computer graphics, entertainment, and art. Artists and designers can now create unique and visually stunning images using GANs, allowing for endless creativity and exploration. GANs have also been used in the fashion industry to generate new clothing designs. By training a GAN on a dataset of fashion images, designers can generate new and unique clothing designs that can be used for inspiration or even produced as real garments. This has the potential to revolutionize the fashion industry by enabling the creation of personalized and on-demand clothing. 6.4.2 Data Augmentation. Data augmentation is a technique used in machine learning to increase the size and diversity of a training dataset. GANs can be used to generate synthetic data that can be added to the original dataset, thereby enhancing the performance of machine learning models. This is particularly useful in scenarios where the availability of labeled data is limited. For example, in the medical field, GANs can be used to generate synthetic medical images that can be added to the training dataset. This can help improve the accuracy of medical image analysis tasks such as tumor detection or disease diagnosis. By augmenting the dataset with synthetic data, the model becomes more robust and generalizes better to unseen data. 6.4.3 Video Generation and Prediction. GANs have also been applied to the generation and prediction of videos. By extending the concept of image generation, GANs can generate realistic and coherent video sequences. This has applications in the entertainment industry, where GANs can be used to create special effects or generate new scenes for movies and video games. In addition to video generation, GANs can also be used for video prediction. By training a GAN on a sequence of video frames, the generator network can be used to predict future frames in the video. This has applications in video compression, where GANs can be used to generate compressed video frames, reducing the size of the video file without significant loss in quality. 6.4.4 Style Transfer and Image Editing. Style transfer is a technique that allows the transfer of artistic styles from one image to another. GANs have been used to achieve impressive style transfer results by learning the style of one image and applying it to another image. This has applications in the field of image editing, where users can apply different artistic styles to their photographs or create unique visual effects. GANs can also be used for image inpainting, which involves filling in missing or corrupted parts of an image. By training a GAN on a dataset of complete images, the generator network can be used to generate plausible and visually coherent completions for missing or corrupted regions in an image. This has applications in image restoration and editing, where damaged or incomplete images can be repaired or enhanced. 6.4.5 Anomaly Detection and Data Cleaning. GANs have shown promise in the field of anomaly detection and data cleaning. By training a GAN on a dataset of normal data, the generator network learns to generate samples that resemble the normal data distribution. Any data point that deviates significantly from the learned distribution can be considered an anomaly. This can be useful in various domains such as fraud detection, cybersecurity, and quality control. Furthermore, GANs can be used for data cleaning by generating synthetic data that fills in missing or corrupted values in a dataset. This can help improve the quality and completeness of the data, leading to more accurate and reliable analysis. In conclusion, generative adversarial networks (GANs) have revolutionized various industries with their ability to generate realistic and high-quality data. From image generation and synthesis to data augmentation and anomaly detection, GANs have opened up new possibilities and have the potential to transform the way we create, analyze, and interpret data. As GANs continue to evolve and improve, we can expect even more exciting applications in the future. 7. Reinforcement learning and neural networks. 7.1 Introduction to reinforcement learning. Reinforcement learning is a subfield of machine learning that focuses on training agents to make sequential decisions in an environment to maximize a cumulative reward. Unlike supervised learning, where the agent is provided with labeled examples, or unsupervised learning, where the agent learns patterns in unlabeled data, reinforcement learning relies on trial and error to learn optimal actions. In reinforcement learning, an agent interacts with an environment by taking actions and receiving feedback in the form of rewards or penalties. The goal of the agent is to learn a policy, which is a mapping from states to actions, that maximizes the expected cumulative reward over time. The agent learns this policy through a process of exploration and exploitation, where it explores different actions to gather information about the environment and exploits its knowledge to make better decisions. The key components of a reinforcement learning system are the agent, the environment, and the reward signal. The agent is the learner or decision maker, while the environment is the external system with which the agent interacts. The reward signal is a scalar value that provides feedback to the agent about the desirability of its actions. The agent's objective is to learn a policy that maximizes the expected cumulative reward. One of the fundamental concepts in reinforcement learning is the Markov decision process (MDP). An MDP is a mathematical framework that models the interaction between an agent and an environment. It consists of a set of states, a set of actions, a transition function that defines the dynamics of the environment, and a reward function that assigns a reward to each state-action pair. The transition function specifies the probability of transitioning from one state to another when an action is taken, while the reward function provides immediate feedback to the agent. To solve an MDP, the agent employs a value function or a Q function. The value function estimates the expected cumulative reward starting from a particular state and following a specific policy. The Q function, on the other hand, estimates the expected cumulative reward starting from a particular state, taking a specific action, and following a specific policy thereafter. The value function and the Q function are used to guide the agent's decision-making process by assigning a value to each state or state-action pair. There are several algorithms used in reinforcement learning, with Q-learning being one of the most popular. Q-learning is a model-free algorithm that learns the optimal Q function through an iterative process of updating the Q values based on the observed rewards. The Q values are initialized randomly and are updated using the Bellman equation, which expresses the relationship between the current Q value, the immediate reward, and the estimated future rewards. Deep Q networks (DQNs) are a variant of Q-learning that uses deep neural networks to approximate the Q function. By using neural networks, DQNs can handle high-dimensional state spaces and learn complex representations of the environment. The neural network takes the state as input and outputs the Q values for each action. The agent selects actions based on an exploration-exploitation strategy, such as epsilon greedy, where it chooses the action with the highest Q value with a certain probability and explores other actions with a lower probability. Reinforcement learning has found applications in various domains, including robotics, game playing, autonomous vehicles, and recommendation systems. In robotics, reinforcement learning can be used to train robots to perform complex tasks, such as grasping objects or navigating through an environment. In game playing, reinforcement learning has achieved remarkable success, with algorithms like AlphaGo defeating world champions in games like Go and chess. In conclusion, reinforcement learning is a powerful paradigm for training agents to make sequential decisions in an environment. By using trial and error, agents can learn optimal policies that maximize cumulative rewards. With the advancements in deep learning and neural networks, reinforcement learning has become even more effective in handling complex tasks in high-dimensional state spaces. The combination of reinforcement learning with neural networks has the potential to revolutionize various industries and pave the way for intelligent systems capable of autonomous decision-making. 7.2 Q-learning and neural networks. Q-learning is a popular reinforcement learning algorithm that has been widely used in various applications. It is a model-free algorithm that allows an agent to learn optimal actions in a given environment by iteratively updating its Q values. Q values represent the expected future rewards an agent can obtain by taking a particular action in a specific state. In traditional Q-learning, the Q values are stored in a table called a Q table. However, as the number of states and actions increases, the size of the Q table becomes impractical. This is where neural networks come into play. By using neural networks as function approximators, we can overcome the limitations of the Q table and handle complex environments with large state and action spaces. 7.2.1 Q-learning with neural networks. In Q-learning with neural networks, instead of using a Q table, we use a neural network to approximate the Q values. The neural network takes the state as input and outputs the Q values for all possible actions. The network is trained to minimize the difference between the predicted Q values and the target Q values. The target Q values are calculated using the Bellman equation, which expresses the optimal Q value of a state-action pair as the sum of the immediate reward and the maximum Q value of the next state. By iteratively updating the Q values based on the Bellman equation, the neural network gradually learns to approximate the optimal Q values. During training, the agent interacts with the environment, observes the current state, takes an action based on an exploration-exploitation strategy, receives a reward, and transitions to the next state. The agent then uses this experience to update the Q values and train the neural network. This process is repeated until the agent converges to an optimal policy. 7.2.2 Deep Q Networks (DQN). Deep Q Networks (DQN) is an extension of Q learning with neural networks that introduce the concept of experience replay and target networks. Experience replay is a technique that stores the agent's experiences, state, action, reward, next state in a replay buffer and samples mini batches of experiences for training. This helps to break the correlation between consecutive experiences and stabilize the learning process. Target networks are used to address the issue of moving targets in Q learning. In traditional Q learning, the Q values are updated based on the current Q values, which can lead to instability. Target networks are copies of the main network that are periodically updated with the weights of the main network. The target network is used to calculate the target Q values during training, providing a more stable learning process. DQN has been successfully applied to various domains, including playing Atari games, controlling robotic systems, and optimizing resource allocation. The combination of deep neural networks and Q learning has proven to be a powerful approach for solving complex reinforcement learning problems. 7.2.3 Applications of Reinforcement Learning with Neural Networks. Reinforcement learning with neural networks has found applications in a wide range of fields. Here are a few notable examples. Game playing. Reinforcement learning with neural networks has been used to train agents that can play complex games, such as chess, Go, and poker. These agents learn to make optimal decisions by playing against themselves or human players, and they have achieved superhuman performance in many cases. Robotics. Neural networks have been used in reinforcement learning to train robots to perform various tasks, such as grasping objects, navigating in complex environments, and even playing sports. By combining sensory inputs with reinforcement learning algorithms, robots can learn to interact with their environment and adapt to different situations. Autonomous vehicles. Reinforcement learning with neural networks has been applied to train autonomous vehicles to make decisions in real time. By using neural networks to process sensor data and predict optimal actions, autonomous vehicles can learn to navigate safely and efficiently in complex traffic scenarios. Finance. Neural networks have been used in reinforcement learning to develop trading strategies and optimize portfolio management. By learning from historical market data and reinforcement signals, neural networks can adapt their trading decisions to changing market conditions and maximize returns. Healthcare. Reinforcement learning with neural networks has been explored in healthcare applications, such as personalized treatment recommendation and disease diagnosis. By learning from patient data and reinforcement signals, neural networks can assist healthcare professionals in making informed decisions and improving patient outcomes. These are just a few examples of the wide range of applications of reinforcement learning with neural networks. As the field continues to advance, we can expect to see even more innovative and impactful applications in the future. In this section, we explored how Q learning can be combined with neural networks to solve reinforcement learning problems. We discussed the concept of Q learning with neural networks, the introduction of Deep Q Networks (DQN), and the applications of reinforcement learning with neural networks in various domains. The combination of reinforcement learning and neural networks has opened up new possibilities for solving complex problems and has the potential to revolutionize many industries. 7.3 Deep Q Networks. Deep Q networks (DQNs) are a type of neural network architecture that combines reinforcement learning with deep learning techniques. They have revolutionized the field of artificial intelligence by achieving remarkable results in complex decision-making tasks. DQNs are particularly effective in solving problems where the optimal action depends on the current state of the environment. 7.3.1 Introduction to Deep Q Networks. Deep Q networks were first introduced by researchers at Google DeepMind in 2013. The key idea behind DQNs is to use a neural network to approximate the Q function, which represents the expected future rewards for each possible action in a given state. By learning this Q function, the DQN can make informed decisions about which actions to take in order to maximize its cumulative reward over time. 7.3.2 Architecture of Deep Q Networks. The architecture of a deep Q network consists of several layers of neurons, with each layer responsible for processing different aspects of the input data. The input to the network is typically the current state of the environment, and the output is a vector of Q values, representing the expected future rewards for each possible action. One of the key features of DQNs is the use of convolutional layers, which are particularly effective in processing high-dimensional input data such as images. These layers help the network extract meaningful features from the input, allowing it to make accurate predictions about the Q values. 7.3.3 Training Deep Q Networks. Training a deep Q network involves a process called experience replay, which is crucial for stabilizing the learning process. Experience replay involves storing the agent's experiences, i.e., state action reward next state tuples, in a replay buffer and randomly sampling from this buffer during training. This helps the network to learn from a diverse set of experiences and reduces the correlation between consecutive samples. During training, the DQN uses a technique called Q-learning to update its Q values. Q-learning involves updating the Q value of the chosen action based on the observed reward and the maximum Q value of the next state. This update is performed iteratively, gradually improving the network's ability to estimate the optimal Q values. 7.3.4 Applications of Deep Q networks. Deep Q networks have been successfully applied to a wide range of domains, including robotics, video games, and autonomous driving. In robotics, DQNs have been used to control robotic arms and perform complex manipulation tasks. In video games, DQNs have achieved superhuman performance in games like Atari and Go. In autonomous driving, DQNs have been used to navigate vehicles in complex environments. One notable application of DQNs is in the field of healthcare. DQNs have been used to develop personalized treatment plans for patients with chronic diseases, such as diabetes and cancer. By learning from historical patient data, DQNs can recommend the most effective treatment options for individual patients, taking into account their unique characteristics and medical history. 7.3.5 Challenges and Future Directions. While Deep Q networks have shown great promise in various domains, they also face several challenges. One challenge is the issue of overestimation of Q values, which can lead to suboptimal policies. Researchers have proposed various techniques, such as double Q learning and dueling architectures, to mitigate this issue. Another challenge is the high computational requirements of training DQNs. Training a DQN can be computationally intensive, especially when dealing with large-scale problems or complex environments. Researchers are actively exploring techniques to improve the efficiency of training DQNs, such as parallelization and distributed computing. In the future, we can expect to see further advancements in the field of Deep Q networks. Researchers are exploring ways to enhance the stability and sample efficiency of DQNs, as well as investigating the combination of DQNs with other reinforcement learning algorithms. Additionally, the application of DQNs to real-world problems, such as healthcare and finance, is an area of active research. Deep Q networks have opened up new possibilities for artificial intelligence and have demonstrated the power of combining deep learning with reinforcement learning. With further advancements in research, DQNs have the potential to revolutionize various industries and contribute to the development of intelligent systems that can make complex decisions in dynamic environments. 7.4 Applications of Reinforcement Learning with Neural Networks. Reinforcement learning is a branch of machine learning that focuses on training agents to make sequential decisions in an environment to maximize a reward signal. It is a powerful technique that has been successfully applied to a wide range of real-world problems. When combined with neural networks, reinforcement learning becomes even more effective, allowing agents to learn complex behaviors and make intelligent decisions. 7.4.1 Game playing. One of the most well-known applications of reinforcement learning with neural networks is in game playing. Deep reinforcement learning algorithms, such as Deep Q networks (DQNs), have achieved remarkable success in playing various games, including classic Atari games and complex board games like Go and chess. In these applications, the neural network acts as a function approximator, mapping the game state to the predicted action values. The agent interacts with the game environment, receiving feedback in the form of rewards or penalties, and uses this information to update the neural network's weights through backpropagation. Over time, the agent learns to make optimal decisions based on the game state, leading to impressive gameplay performance. 7.4.2 Robotics. Reinforcement learning with neural networks has also found extensive applications in robotics. By combining neural networks with reinforcement learning algorithms, robots can learn to perform complex tasks and adapt to different environments. For example, in autonomous navigation, a robot can learn to navigate through a maze or a cluttered environment by using reinforcement learning. The neural network can take sensory inputs from the robot's sensors and output control signals to move the robot in the desired direction. Through trial and error, the robot learns to avoid obstacles, find optimal paths, and reach its goal efficiently. Furthermore, reinforcement learning with neural networks has been used in robotic manipulation tasks, such as grasping objects or assembling parts. By training the robot through reinforcement learning, it can learn to manipulate its limbs or grippers to perform precise actions, improving its dexterity and adaptability. 7.4.3 Autonomous vehicles. Autonomous vehicles are another area where reinforcement learning with neural networks has shown great promise. By combining reinforcement learning with perception systems, autonomous vehicles can learn to navigate complex traffic scenarios and make safe driving decisions. The neural network can process inputs from various sensors, such as cameras, lidars, and radars, to perceive the surrounding environment. It can then output control signals to steer the vehicle, accelerate, or brake. Through reinforcement learning, the vehicle can learn to make appropriate decisions based on the traffic situation, such as changing lanes, merging, or avoiding collisions. Reinforcement learning with neural networks enables autonomous vehicles to adapt to different driving conditions and learn from real-world experiences. This approach has the potential to improve the safety and efficiency of autonomous driving systems. 7.4.4 Finance and Trading. Reinforcement learning with neural networks has also found applications in the field of finance and trading. By using historical market data, agents can learn to make optimal trading decisions and maximize profits. The neural network can analyze market indicators, such as stock prices, trading volumes, and technical indicators, to predict future price movements. Based on these predictions, the agent can decide when to buy or sell assets. Through reinforcement learning, the agent can learn to optimize its trading strategy and adapt to changing market conditions. This application of reinforcement learning with neural networks has the potential to improve trading strategies and enhance investment decision-making in financial markets. 7.4.5 Healthcare. Reinforcement learning with neural networks has also shown promise in healthcare applications. It can be used to optimize treatment plans, personalize patient care, and improve medical decision-making. For example, in personalized medicine, reinforcement learning can be used to determine the optimal dosage of medication for individual patients based on their specific characteristics and response to treatment. The neural network can learn from patient data and feedback to adjust the dosage and maximize the desired treatment outcome. In addition, reinforcement learning with neural networks can be applied to medical imaging analysis, such as detecting and classifying diseases from medical images. The neural network can learn to identify patterns and features in the images to make accurate diagnoses. These applications of reinforcement learning with neural networks have the potential to revolutionize healthcare by improving treatment outcomes and reducing medical errors. Conclusion. Reinforcement learning with neural networks has proven to be a powerful combination for solving complex problems in various domains. From game playing to robotics, autonomous vehicles to finance, and healthcare to many other fields, the applications of reinforcement learning with neural networks are vast and promising. By leveraging the ability of neural networks to learn from data and make intelligent decisions, reinforcement learning enables agents to adapt and optimize their behavior in dynamic environments. This opens up new possibilities for automation, optimization, and decision-making in a wide range of industries. As research and development in reinforcement learning and neural networks continue to advance, we can expect to see even more exciting applications and breakthroughs in the future. The combination of these two technologies holds the potential to revolutionize industries, improve efficiency, and enhance our daily lives. 8. Transfer learning in neural networks. 8.1 Introduction to transfer learning. Transfer learning is a powerful technique in the field of artificial neural networks that allows us to leverage knowledge gained from one task and apply it to another related task. It is based on the idea that the knowledge learned by a neural network on one task can be transferred and used as a starting point for learning a new task. This approach has gained significant attention and popularity in recent years due to its ability to improve the performance and efficiency of neural networks, especially in scenarios where limited labeled data is available. 8.1.1 The need for transfer learning. In traditional machine learning approaches, models are trained from scratch for each specific task. This process requires a large amount of labeled data and computational resources. However, in many real-world scenarios, obtaining a large labeled dataset can be challenging and time-consuming. Transfer learning addresses this issue by allowing us to reuse the knowledge learned from a source task and apply it to a target task, even when the two tasks are not identical. Transfer learning is particularly useful in situations where the source and target tasks share some common underlying patterns or features. By leveraging the knowledge gained from the source task, the neural network can start with a better initialization and learn more efficiently on the target task. This can lead to faster convergence, improved generalization, and better overall performance. 8.1.2 How transfer learning works. Transfer learning involves two main steps: pre-training and fine-tuning. In the pre-training phase, a neural network is trained on a large dataset from the source task. This initial training allows the network to learn general features and patterns that are useful across different tasks. The pre-trained network captures a rich representation of the input data, which can be transferred to the target task. In the fine-tuning phase, the pre-trained network is further trained on a smaller dataset from the target task. The network's parameters are adjusted to adapt to the specific characteristics of the target task. The idea is to retain the learned knowledge from the source task while allowing the network to specialize and refine its predictions for the target task. Fine-tuning helps the network to adapt to the nuances and specific requirements of the target task, leading to improved performance. 8.1.3 Benefits of transfer learning. Transfer learning offers several benefits in the context of artificial neural networks. Improved training efficiency. By starting with a pre-trained network, the training process on the target task can be significantly faster and more efficient. The network has already learned general features from the source task, reducing the need for extensive training on the target task. Better generalization. Transfer learning helps neural networks to generalize better by leveraging the knowledge learned from the source task. The pre-trained network captures useful representations of the input data, which can be applied to the target task, even with limited labeled data. Addressing data scarcity. In scenarios where labeled data is scarce or expensive to obtain, transfer learning can be a valuable approach. By reusing the knowledge from the source task, the network can achieve good performance even with a smaller labeled dataset for the target task. Domain adaptation. Transfer learning is particularly useful when the source and target tasks belong to different domains. The pre-trained network can adapt its learned representations to the target domain, allowing the network to perform well even with domain shifts. Reduced computational resources. Since transfer learning allows us to start with a pre-trained network, the need for extensive computational resources is reduced. This makes it feasible to apply neural networks to resource-constrained environments. 8.1.4 Challenges and Considerations. While transfer learning offers numerous advantages, there are also challenges and considerations to keep in mind. Task similarity. The success of transfer learning depends on the similarity between the source and target tasks. If the tasks are too dissimilar, the transferred knowledge may not be relevant or useful for the target task. Overfitting. Fine-tuning a pre-trained network on a small target dataset can lead to overfitting. Careful regularization techniques and monitoring of the training process are necessary to prevent overfitting and ensure good generalization. Layer compatibility. The architecture of the pre-trained network and the target network should be compatible. The layers that are shared between the two networks should have similar input and output dimensions to facilitate knowledge transfer. Bias and dataset bias. Transfer learning can inherit biases from the source task, which may not be desirable for the target task. Additionally, if the source dataset is biased, it can introduce biases in the target task as well. Choosing the right layers. Selecting the appropriate layers to transfer knowledge from the source task to the target task is crucial. Higher-level layers tend to capture more task-specific information, while lower-level layers capture more general features. Conclusion. Transfer learning is a valuable technique in the field of artificial neural networks that allows us to leverage knowledge from one task and apply it to another related task. By reusing the learned representations and features, transfer learning improves training efficiency, generalization, and performance, especially in scenarios with limited labeled data. However, careful consideration of task similarity, overfitting, layer compatibility, biases, and layer selection is necessary to ensure successful transfer learning. With its potential to address data scarcity and improve the efficiency of neural networks, transfer learning is a promising approach for various real-world applications. 8.2 Transfer learning techniques. Transfer learning is a powerful technique in the field of artificial neural networks that allows us to leverage knowledge gained from one task and apply it to another related task. It enables the transfer of learned features or representations from a source domain to a target domain, thereby reducing the need for large amounts of labeled data and training time. In this section, we will explore various transfer learning techniques and their applications in neural networks. 8.2.1 Pre-trained models. One common approach to transfer learning is to use pre-trained models. These models are typically trained on large-scale datasets, such as ImageNet, which contain millions of labeled images. By using a pre-trained model as a starting point, we can benefit from the knowledge it has acquired during training. The lower layers of the pre-trained model capture low-level features like edges and textures, which are generally applicable to many tasks. We can then fine-tune the higher layers of the model on our specific task, allowing it to learn task-specific features. Pre-trained models are available for various types of neural networks, including convolutional neural networks, CNNs, recurrent neural networks, RNNs, and generative adversarial networks, GANs. These models have been trained on diverse datasets and have achieved state-of-the-art performance on a wide range of tasks. By using pre-trained models, we can save significant time and computational resources that would otherwise be required to train a model from scratch. 8.2.2 Feature extraction. Another transfer learning technique is feature extraction. In this approach, we use a pre-trained model as a fixed feature extractor. We remove the last few layers of the model, which are responsible for making predictions, and replace them with new layers that are specific to our task. By freezing the weights of the pre-trained layers, we ensure that they are not updated during training, and only the new layers are trained on our task-specific data. Feature extraction is particularly useful when we have a small dataset for our target task. By leveraging the learned representations from the pre-trained model, we can benefit from the generalization power of the model while avoiding overfitting. This technique is commonly used in computer vision tasks, where the lower layers of a CNN capture generic image features that can be useful for a wide range of tasks. 8.2.3 Fine-tuning. Fine-tuning is a transfer learning technique that involves updating the weights of a pre-trained model on a new task-specific dataset. Unlike feature extraction, which only updates the weights of the new layers, fine-tuning allows us to update the weights of both the pre-trained layers and the new layers. This approach is beneficial when we have a relatively large dataset for our target task. To perform fine-tuning, we typically start by freezing the weights of the pre-trained layers and train the new layers on our task-specific data. Once the new layers have converged, we gradually unfreeze the pre-trained layers and continue training the entire model. This allows the model to adapt its learned representations to the new task while retaining the knowledge gained from the pre-trained model. Fine-tuning is commonly used in natural language processing tasks, where pre-trained language models, such as BERT and GPT, have been trained on large corpora of text. By fine-tuning these models on specific tasks like sentiment analysis or named entity recognition, we can achieve state-of-the-art performance with minimal training time. 8.2.4 Domain adaptation. Domain adaptation is a transfer learning technique that addresses the problem of differences between the source and target domains. In many real-world scenarios, the distribution of data in the source domain may differ from that in the target domain, leading to a degradation in performance when directly applying a pre-trained model. To overcome this challenge, domain adaptation techniques aim to align the feature distributions between the source and target domains. This can be achieved through various methods, such as adversarial training, where a domain discriminator is trained to distinguish between source and target data, and the model is trained to confuse the discriminator by generating domain invariant features. Domain adaptation is particularly useful in tasks where labeled data in the target domain is scarce or expensive to obtain. By leveraging knowledge from a related source domain, we can improve the performance of our model on the target domain. 8.2.5 Multitask learning. Multitask learning is a transfer learning technique that involves training a neural network on multiple related tasks simultaneously. By jointly learning multiple tasks, the model can leverage the shared knowledge and correlations between the tasks, leading to improved performance on each individual task. In multitask learning, the lower layers of the neural network are shared across all tasks, while each task has its own task-specific layers. The shared layers capture the common features across tasks, while the task-specific layers capture the unique features required for each task. This approach is particularly useful when we have limited labeled data for each individual task but abundant labeled data for the combined tasks. By training the model jointly, we can effectively transfer knowledge between tasks and improve the overall performance. 8.2.6 Applications of transfer learning. Transfer learning has been successfully applied to a wide range of domains and tasks. In computer vision, pre-trained models have been used for image classification, object detection, and image segmentation tasks. In natural language processing, pre-trained language models have been used for sentiment analysis, text classification, and machine translation tasks. In speech recognition, pre-trained models have been used for speech-to-text conversion and speaker identification tasks. Transfer learning has also found applications in healthcare, where models pre-trained on large medical imaging datasets have been used for disease diagnosis and medical image analysis. In finance, transfer learning has been used for stock market prediction and fraud detection. In autonomous driving, transfer learning has been used for object detection and lane detection. The versatility and effectiveness of transfer learning make it a valuable tool in the arsenal of neural network practitioners. By leveraging the knowledge acquired from previous tasks, we can accelerate the development of new models, improve performance, and tackle real-world problems with limited labeled data. 8.3 Fine-tuning neural networks. Fine-tuning is a technique used in neural networks to improve the performance of a pre-trained model on a new task or dataset. It involves taking a pre-trained model and making small adjustments to its parameters to adapt it to the new task. Fine-tuning is particularly useful when the new task is similar to the task the model was originally trained on. 8.3.1 The need for fine-tuning. When training a neural network from scratch, it requires a large amount of labeled data and computational resources. However, in many real-world scenarios, obtaining such resources may not be feasible. Fine-tuning provides a solution to this problem by leveraging the knowledge learned from a pre-trained model and applying it to a new task with limited data. Fine-tuning is especially effective in transfer learning, where a model trained on a source task is used as a starting point for a target task. By fine-tuning the pre-trained model, we can quickly adapt it to the target task and achieve better performance with less training data. 8.3.2 Fine-tuning process. The process of fine-tuning a neural network involves several steps. Selecting a pre-trained model. The first step is to choose a pre-trained model that is suitable for the target task. The pre-trained model should have been trained on a similar task or dataset to ensure that it has learned relevant features. Freezing the initial layers. In most cases, the initial layers of the pre-trained model are responsible for learning low-level features such as edges and textures. These layers are usually generic and can be reused for the new task. By freezing these layers, we prevent them from being modified during the fine-tuning process. Adding new layers. To adapt the pre-trained model to the new task, we add new layers on top of the frozen layers. These new layers are responsible for learning task-specific features. The number and architecture of these layers depend on the complexity of the target task. Training the new layers. Once the new layers have been added, we train the model using the labeled data from the target task. During this training phase, only the parameters of the new layers are updated, while the parameters of the frozen layers remain unchanged. Fine-tuning the entire model. After training the new layers, we can further improve the performance of the model by fine-tuning the entire network. In this step, we unfreeze the frozen layers and continue training the model using a smaller learning rate. This allows the model to adjust its parameters based on the new task while still retaining the knowledge learned from the pre-trained model. 8.3.3 Benefits of fine-tuning. Fine-tuning offers several benefits in the context of neural networks. Improved performance. By leveraging the knowledge learned from a pre-trained model, fine-tuning can significantly improve the performance of a model on a new task. The pre-trained model has already learned useful features, which can be adapted to the target task with minimal training. Reduced training time. Fine-tuning allows us to train a model on a new task with limited data, saving time and computational resources. Instead of training a model from scratch, we can build upon the knowledge already present in the pre-trained model. Transferability of knowledge. Fine-tuning enables the transfer of knowledge from one task to another. The pre-trained model captures general patterns and features that are applicable across tasks. By fine-tuning, we can transfer this knowledge to a new task and achieve good performance even with limited data. Avoiding overfitting. Fine-tuning a pre-trained model helps in avoiding overfitting, especially when the target task has limited training data. The pre-trained model acts as a regularizer, preventing the model from memorizing the training data and generalizing better to unseen data. 8.3.4 Fine-tuning best practices. To achieve the best results when fine-tuning a neural network, it is important to follow some best practices. Choose a suitable pre-trained model. The choice of the pre-trained model should be based on the similarity between the source and target tasks. The pre-trained model should have learned relevant features that can be adapted to the target task. Freeze the initial layers. Freezing the initial layers of the pre-trained model helps in retaining the learned features and prevents them from being modified during the fine-tuning process. This is particularly useful when the target task shares similar low-level features with the source task. Use a smaller learning rate. When fine-tuning the entire model, it is recommended to use a smaller learning rate compared to the initial training phase. This allows the model to make smaller adjustments to its parameters and avoid catastrophic forgetting of the previously learned knowledge. Regularize the model. Regularization techniques such as dropout or weight decay can be applied during fine-tuning to prevent overfitting. These techniques help in generalizing the model to unseen data and improving its performance on the target task. 8.3.5 Fine-tuning examples. Fine-tuning has been successfully applied in various domains and tasks. Some examples include image classification. Pre-trained models trained on large-scale image classification datasets such as ImageNet have been fine-tuned for specific image classification tasks. By fine-tuning the pre-trained models, researchers and practitioners have achieved state-of-the-art performance on various image classification benchmarks. Natural language processing. Pre-trained language models such as BERT and GPT have been fine-tuned for specific natural language processing tasks such as sentiment analysis, named entity recognition, and question answering. Fine-tuning these models has led to significant improvements in performance on these tasks. Object detection. Pre-trained models such as faster RCNN and YOLO have been fine-tuned for object detection tasks in computer vision. By fine-tuning these models on specific datasets, researchers have achieved accurate and efficient object detection systems. Speech recognition. Pre-trained models trained on large-scale speech datasets have been fine-tuned for speech recognition tasks. Fine-tuning these models has improved the accuracy of speech recognition systems, especially in low-resource scenarios. In conclusion, fine-tuning is a powerful technique in neural networks that allows us to adapt pre-trained models to new tasks with limited data. By leveraging the knowledge learned from the pre-trained model, fine-tuning improves performance, reduces training time, and enables the transfer of knowledge across tasks. Following best practices and considering specific examples, fine-tuning can be effectively applied in various domains and tasks. 8.4 Applications of transfer learning in neural networks. Transfer learning, a technique that allows the knowledge gained from one task to be applied to another related task, has revolutionized the field of artificial neural networks. By leveraging pre-trained models and transferring their learned features, transfer learning has significantly improved the performance and efficiency of neural networks across various domains. In this section, we will explore some of the exciting applications of transfer learning in neural networks. 8.4.1 Image classification. Image classification is one of the most common applications of transfer learning in neural networks. With the availability of large-scale image datasets and pre-trained models such as VGGNet, ResNet, and Inception, transfer learning has become a powerful tool for building accurate image classifiers. By using a pre-trained model as a feature extractor, the lower layers of the network can capture general image features like edges, textures, and shapes. These features can then be fed into a new classifier, which is trained on a smaller dataset specific to the target task. This approach not only reduces the need for large labeled datasets but also improves the generalization and speed of training. 8.4.2 Object detection. Object detection, the task of identifying and localizing objects within an image, has also benefited greatly from transfer learning. By utilizing pre-trained models like faster RCNN, YOLO, or SSD, transfer learning enables the detection of objects in real-time applications. The pre-trained models provide a strong foundation for learning object features, and by fine-tuning the network on a smaller dataset specific to the target objects, the model can quickly adapt to the new task. Transfer learning in object detection has found applications in various domains, including autonomous driving, surveillance systems, and robotics. 8.4.3 Natural language processing. Transfer learning has made significant contributions to natural language processing (NLP) tasks as well. Language models such as BERT, GPT, and Elmo have been pre-trained on large corpora of text data, enabling them to capture rich semantic and syntactic information. These pre-trained models can then be fine-tuned on specific NLP tasks such as sentiment analysis, named entity recognition, or question answering. Transfer learning in NLP has not only improved the accuracy of these tasks but has also reduced the need for large labeled datasets, making it easier to develop NLP applications in various domains. 8.4.4 Speech recognition. Speech recognition, the task of converting spoken language into written text, has seen remarkable advancements with the help of transfer learning. Pre-trained models like Deep Speech and Listen, Attend Spell (LAS), have been trained on large speech datasets, allowing them to learn phonetic and linguistic features. By fine-tuning these models on specific speech recognition tasks, such as voice commands or transcription, transfer learning has improved the accuracy and robustness of speech recognition systems. This has led to the widespread adoption of speech recognition in applications like virtual assistants, transcription services, and voice-controlled devices. 8.4.5 Medical diagnosis. Transfer learning has also found applications in the field of medical diagnosis. By leveraging pre-trained models trained on large medical image datasets, such as mammograms or MRI scans, transfer learning enables the development of accurate diagnostic systems. These pre-trained models can capture complex patterns and features indicative of various diseases or abnormalities. By fine-tuning the models on specific medical imaging tasks, transfer learning can assist doctors in diagnosing diseases like cancer, Alzheimer's, or cardiovascular conditions. This not only improves the accuracy of diagnosis but also reduces the time and cost associated with manual interpretation of medical images. 8.4.6 Anomaly detection. Anomaly detection, the task of identifying rare or abnormal instances within a dataset, has benefited from transfer learning techniques as well. By utilizing pre-trained models trained on normal data, transfer learning enables the detection of anomalies in various domains, such as cybersecurity, fraud detection, or predictive maintenance. The pre-trained models can capture the normal patterns and features present in the data, allowing them to identify deviations from the norm. By fine-tuning the models on specific anomaly detection tasks, transfer learning can improve the accuracy and efficiency of detecting anomalies, thereby enhancing the security and reliability of systems. Transfer learning has proven to be a powerful technique in the field of artificial neural networks, enabling the development of more accurate and efficient models across various domains. By leveraging pre-trained models and transferring their learned features, transfer learning reduces the need for large labeled datasets, improves generalization, and speeds up the training process. From image classification and object detection to natural language processing and medical diagnosis, transfer learning has revolutionized the capabilities of neural networks and opened up new possibilities for solving complex real-world problems. 9. Neural network optimization. 9.1 Gradient descent and optimization algorithms. In the previous chapters, we have discussed the architecture and training of various types of neural networks. However, training a neural network involves finding the optimal set of weights and biases that minimize the error or loss function. This process is known as optimization. One of the most commonly used optimization algorithms in neural networks is gradient descent. 9.1.1 Introduction to gradient descent. Gradient descent is an iterative optimization algorithm used to minimize the loss function of a neural network. It works by adjusting the weights and biases of the network in the direction of steepest descent of the loss function. The idea behind gradient descent is to update the parameters of the network in small steps, gradually approaching the minimum of the loss function. The gradient descent algorithm calculates the gradient of the loss function with respect to each parameter of the network. The gradient represents the direction of the steepest descent of the loss function. By taking the negative gradient, we can move in the direction of steepest descent. The size of the steps taken in each iteration is controlled by the learning rate, which determines the magnitude of the parameter updates. 9.1.2 Batch gradient descent. Batch gradient descent is the simplest form of gradient descent. In this method, the entire training dataset is used to calculate the gradient of the loss function. The weights and biases of the network are then updated based on the average gradient over the entire dataset. Batch gradient descent guarantees convergence to the global minimum of the loss function, but it can be computationally expensive for large datasets. 9.1.3 Stochastic gradient descent. Stochastic gradient descent (SGD) is a variation of gradient descent that updates the weights and biases of the network after each individual training example. Unlike batch gradient descent, SGD uses only a single training example at a time to calculate the gradient. This makes SGD computationally more efficient, especially for large datasets. However, the updates can be noisy and may not converge to the global minimum. 9.1.4 Mini-batch gradient descent. Mini-batch gradient descent is a compromise between batch gradient descent and stochastic gradient descent. In this method, the training dataset is divided into small batches, and the weights and biases of the network are updated based on the average gradient over each batch. Mini-batch gradient descent combines the efficiency of SGD with the stability of batch gradient descent. The batch size is a hyperparameter that needs to be tuned for optimal performance. 9.1.5 Optimization algorithms. While gradient descent is a fundamental optimization algorithm, there are several variations and enhancements that have been developed to improve its performance. Some of the commonly used optimization algorithms in neural networks include 9.1.5.1 Momentum. Momentum is an optimization algorithm that helps accelerate gradient descent in the relevant direction and dampens oscillations. It introduces a momentum term that accumulates the gradient over time and adds a fraction of the previous update to the current update. This allows the algorithm to overcome small local minima and converge faster. 9.1.5.2 AdaGrad. AdaGrad is an adaptive learning rate optimization algorithm that adjusts the learning rate for each parameter based on the historical gradients. It decreases the learning rate for frequently occurring parameters and increases it for infrequently occurring parameters. AdaGrad is particularly useful for sparse data and can converge quickly. 9.1.5.3 RMS Prop. RMS-prop is another adaptive learning rate optimization algorithm that addresses the diminishing learning rate problem of eta grad. It uses an exponentially weighted moving average of the squared gradients to normalize the learning rate. RMS-prop prevents the learning rate from becoming too small and helps converge faster. 9.1.5.4 ADAM. ADAM, Adaptive Moment Estimation, is a popular optimization algorithm that combines the benefits of momentum and RMS-prop. It uses both the first-order moment, the average of the gradients, and the second-order moment, the average of the squared gradients, to adaptively adjust the learning rate. ADAM is known for its efficiency and robustness in a wide range of neural network architectures. 9.1.6 Choosing the right optimization algorithm. The choice of optimization algorithm depends on various factors such as the size of the dataset, the complexity of the neural network, and the specific problem at hand. While gradient descent is a good starting point, it may not always be the most efficient or effective algorithm for a given task. It is important to experiment with different optimization algorithms and hyperparameters to find the best combination for your neural network. Additionally, monitoring the training progress and evaluating the performance on validation data can help in selecting the most suitable optimization algorithm. In conclusion, gradient descent and its variations are essential tools for optimizing neural networks. They allow us to find the optimal set of weights and biases that minimize the loss function. By understanding the different optimization algorithms and their characteristics, we can improve the training efficiency and performance of our neural networks. 9.2 Regularization Techniques. Regularization is a crucial aspect of training artificial neural networks. It helps prevent overfitting, a common problem in machine learning where the model becomes too complex and starts to memorize the training data instead of learning the underlying patterns. Regularization techniques introduce additional constraints to the model, encouraging it to generalize better to unseen data. In this section, we will explore some popular regularization techniques used in neural networks. 9.2.1 L1 and L2 Regularization. L1 and L2 regularization, also known as weight decay, are two commonly used techniques to prevent overfitting. These techniques add a regularization term to the loss function, which penalizes large weights in the network. L1 regularization adds the absolute value of the weights to the loss function, encouraging the model to have sparse weights. This means that some weights may become zero, effectively reducing the complexity of the model. L2 regularization, on the other hand, adds the squared value of the weights to the loss function. This encourages the model to have small weights overall, but without forcing any weights to become exactly zero. The regularization term is controlled by a hyperparameter called the regularization strength or lambda. A higher value of lambda will result in stronger regularization, leading to simpler models with smaller weights. 9.2.2 Dropout. Dropout is a regularization technique that randomly sets a fraction of the input units to zero during training. This helps prevent the network from relying too heavily on any single input feature, forcing it to learn more robust and generalizable representations. During each training iteration, dropout randomly selects a subset of the input units to be dropped out. The fraction of units dropped out is determined by a hyperparameter called the dropout rate. Common dropout rates range from 0.2 to 0.5. Dropout can be applied to both the input and hidden layers of a neural network. It is important to note that dropout is only applied during training and not during inference or testing. 9.2.3 Batch Normalization. Batch normalization is a technique that normalizes the activations of each layer in a neural network. It helps address the problem of internal covariate shift, where the distribution of the inputs to each layer changes during training. By normalizing the inputs to each layer, batch normalization reduces the dependence of the network on the scale and distribution of the input data. This allows for faster and more stable training, as the network becomes less sensitive to the initialization of the weights. Batch normalization is typically applied after the linear transformation and activation function of each layer. It introduces additional learnable parameters, known as the scale and shift parameters, which allow the network to learn the optimal normalization for each layer. 9.2.4 Early Stopping. Early stopping is a simple yet effective regularization technique that helps prevent overfitting by monitoring the validation loss during training. The idea behind early stopping is to stop training when the validation loss starts to increase, indicating that the model is starting to overfit the training data. To implement early stopping, the training process is divided into epochs. After each epoch, the validation loss is computed. If the validation loss does not improve for a certain number of epochs, training is stopped, and the model with the lowest validation loss is selected as the final model. Early stopping helps find the balance between underfitting and overfitting. It allows the model to train for a sufficient number of epochs to learn the underlying patterns in the data but prevents it from continuing to train when it starts to memorize the training examples. 9.2.5 Data Augmentation. Data augmentation is a regularization technique commonly used in computer vision tasks. It involves applying random transformations to the training data, such as rotations, translations, and flips, to create additional training examples. By augmenting the training data, data augmentation helps increase the diversity and variability of the training set. This allows the model to learn more robust and generalizable features, as it is exposed to a wider range of variations in the data. Data augmentation is particularly useful when the training data is limited or imbalanced. It helps prevent overfitting by artificially increasing the size of the training set and reducing the risk of the model memorizing specific examples. 9.2.6 Early stopping. Early stopping is a simple yet effective regularization technique that helps prevent overfitting by monitoring the validation loss during training. The idea behind early stopping is to stop training when the validation loss starts to increase, indicating that the model is starting to overfit the training data. To implement early stopping, the training process is divided into epochs. After each epoch, the validation loss is computed. If the validation loss does not improve for a certain number of epochs, training is stopped, and the model with the lowest validation loss is selected as the final model. Early stopping helps find the balance between underfitting and overfitting. It allows the model to train for a sufficient number of epochs to learn the underlying patterns in the data but prevents it from continuing to train when it starts to memorize the training examples. 9.2.7 Summary. Regularization techniques play a crucial role in training artificial neural networks. They help prevent overfitting and improve the generalization ability of the models. In this section, we explored several popular regularization techniques, including L1 and L2 regularization, dropout, batch normalization, and data augmentation. Each technique introduces additional constraints or modifications to the network, encouraging it to learn more robust and generalizable representations. By incorporating these regularization techniques into the training process, we can improve the performance and reliability of neural networks in various applications. 9.3 Hyperparameter tuning. Hyperparameter tuning is a crucial step in optimizing the performance of artificial neural networks. Hyperparameters are parameters that are not learned during the training process but are set before training begins. These parameters control the behavior and performance of the neural network, such as the learning rate, the number of hidden layers, the number of neurons in each layer, and the regularization strength. The process of hyperparameter tuning involves finding the optimal values for these hyperparameters that result in the best performance of the neural network. It is important to note that there is no one-size-fits-all approach to hyperparameter tuning, as the optimal values can vary depending on the specific problem and dataset. 9.3.1 Importance of hyperparameter tuning. Hyperparameter tuning plays a crucial role in achieving the best performance of artificial neural networks. The choice of hyperparameters can significantly impact the convergence speed, generalization ability, and overall accuracy of the neural network. If the hyperparameters are not properly tuned, the neural network may suffer from issues such as overfitting or underfitting. Overfitting occurs when the neural network performs well on the training data but fails to generalize to new, unseen data. Underfitting, on the other hand, happens when the neural network fails to capture the underlying patterns in the data, resulting in poor performance. By carefully tuning the hyperparameters, we can find the optimal balance between model complexity and generalization ability. This allows the neural network to learn the underlying patterns in the data effectively and make accurate predictions on unseen data. 9.3.2 Hyperparameter search methods. There are several methods available for hyperparameter tuning, each with its own advantages and disadvantages. Some of the commonly used methods include grid search. Grid search is a simple and systematic method for hyperparameter tuning. It involves defining a grid of possible values for each hyperparameter and exhaustively searching through all possible combinations. The performance of the neural network is evaluated for each combination, and the hyperparameter values that yield the best performance are selected. Grid search is easy to implement and guarantees that the optimal hyperparameter values will be found within the search space. However, it can be computationally expensive, especially when dealing with a large number of hyperparameters or a large search space. Random search. Random search is another popular method for hyperparameter tuning. Instead of exhaustively searching through all possible combinations, random search randomly samples hyperparameter values from a predefined search space. The performance of the neural network is evaluated for each set of hyperparameter values, and the best performing set is selected. Random search is computationally more efficient than grid search, as it does not require evaluating all possible combinations. It also has the advantage of being able to explore a wider range of hyperparameter values. However, there is no guarantee that the optimal hyperparameter values will be found within the search space. Bayesian optimization. Bayesian optimization is a more advanced method for hyperparameter tuning that uses probabilistic models to guide the search process. It builds a surrogate model of the objective function, e.g., validation accuracy, and uses this model to make informed decisions about which hyperparameter values to evaluate next. Bayesian optimization is particularly useful when the search space is large or when evaluating the performance of the neural network is computationally expensive. It has the advantage of being able to adaptively explore the search space based on the observed performance, leading to faster convergence to the optimal hyperparameter values. 9.3.3 Cross-validation. Cross-validation is a widely used technique for evaluating the performance of a neural network during hyperparameter tuning. It involves splitting the available data into multiple subsets or folds. The neural network is trained on a subset of the data and evaluated on the remaining fold. This process is repeated for each fold, and the average performance across all folds is used as the evaluation metric. Cross-validation helps to provide a more robust estimate of the neural network's performance by reducing the impact of data variability. It also helps to prevent overfitting to a specific subset of the data. During hyperparameter tuning, Cross-validation is typically used to compare the performance of different hyperparameter settings. The hyperparameter values that result in the best average performance across all folds are selected as the optimal values. 9.3.4 Automated hyperparameter tuning. Hyperparameter tuning can be a time-consuming and iterative process, especially when dealing with a large number of hyperparameters or a large search space. To alleviate this burden, automated hyperparameter tuning techniques have been developed. One such technique is called hyperparameter optimization, which uses machine learning algorithms to automatically search for the optimal hyperparameter values. These algorithms leverage the performance feedback from previous iterations to guide the search process and quickly converge to the optimal values. Popular hyperparameter optimization libraries, such as Optuna, HyperOpt, and Scikit-Optimize, provide efficient and automated methods for hyperparameter tuning. These libraries offer a range of optimization algorithms, including Bayesian optimization, random search, and genetic algorithms, to find the best hyperparameter values for the neural network. Automated hyperparameter tuning not only saves time and effort but also helps to avoid human bias and intuition in the hyperparameter selection process. It allows for a more systematic and unbiased exploration of the hyperparameter search space, leading to improved neural network performance. Conclusion. Hyperparameter tuning is a critical step in optimizing the performance of artificial neural networks. By carefully selecting the right hyperparameter values, we can improve the convergence speed, generalization ability, and overall accuracy of the neural network. Various methods, such as grid search, random search, and Bayesian optimization, can be used to search for the optimal hyperparameter values. Cross-validation is commonly employed to evaluate the performance of different hyperparameter settings. Automated hyperparameter tuning techniques further streamline the process and help to quickly converge to the optimal values. With the right hyperparameter tuning approach, we can unlock the full potential of artificial neural networks and achieve superior performance in various applications. 9.4 Optimizing neural network performance. Optimizing the performance of neural networks is crucial for achieving accurate and efficient results in various applications. In this section, we will explore different techniques and strategies to enhance the performance of neural networks. 9.4.1 Data preprocessing. Data preprocessing plays a vital role in optimizing neural network performance. It involves transforming raw data into a format that is suitable for training the network. Some common preprocessing techniques include 9.4.1.1 Data cleaning. Data cleaning involves removing or correcting any errors, inconsistencies, or missing values in the dataset. This step ensures that the neural network receives clean and reliable input data, which can significantly improve its performance. 9.4.1.2 Data normalization. Data normalization is the process of scaling the input features to a standard range. This technique prevents certain features from dominating the learning process and helps the network converge faster. Common normalization techniques include min-max scaling and z-score normalization. 9.4.1.3 Feature selection. Feature selection involves identifying the most relevant features from the dataset. By selecting only the essential features, we can reduce the dimensionality of the input space, which can lead to faster training and improved generalization. 9.4.1.4 Data augmentation. Data augmentation is a technique used to artificially increase the size of the training dataset by applying various transformations to the existing data. This technique helps to reduce overfitting and improves the network's ability to generalize to unseen data. 9.4.2 Model architecture. The architecture of a neural network plays a crucial role in its performance. Here are some strategies to optimize the model architecture. 9.4.2.1 Network depth and width. The depth and width of a neural network refer to the number of layers and the number of neurons in each layer, respectively. Increasing the depth and width of the network can improve its capacity to learn complex patterns. However, it is essential to strike a balance to prevent overfitting and excessive computational complexity. 9.4.2.2 Regularization techniques. Regularization techniques such as L1 and L2 regularization, dropout, and batch normalization can help prevent overfitting and improve the generalization ability of the network. These techniques introduce constraints or modifications to the network's parameters, making it more robust and less prone to overfitting. 9.4.2.3 Network initialization. Proper initialization of the network's weights can significantly impact its performance. Techniques such as Xavier and He initialization ensure that the weights are initialized in a way that facilitates efficient learning and prevents the vanishing or exploding gradient problems. 9.4.3 Training strategies. The training process of a neural network can be optimized using various strategies. Here are some commonly used techniques. 9.4.3.1 Learning rate scheduling. The learning rate determines the step size at which the network's weights are updated during training. Using a fixed learning rate may lead to slow convergence or overshooting. Learning rate scheduling techniques, such as reducing the learning rate over time or using adaptive learning rates, can help improve the training process. 9.4.3.2 Early stopping. Early stopping is a technique used to prevent overfitting by monitoring the network's performance on a validation set during training. Training is stopped when the validation loss starts to increase, indicating that the network has reached its optimal performance. 9.4.3.3 Batch size. The batch size determines the number of samples processed before updating the network's weights. Choosing an appropriate batch size can impact the convergence speed and generalization ability of the network. Larger batch sizes can lead to faster convergence but may sacrifice generalization, while smaller batch sizes can improve generalization but increase training time. 9.4.4 Hyperparameter tuning. Hyperparameters are parameters that are not learned during the training process but are set before training begins. Optimizing hyperparameters is crucial for achieving optimal performance. Techniques such as grid search, random search, and Bayesian optimization can be used to find the best combination of hyperparameters for a given neural network. 9.4.5 Regular monitoring and evaluation. Once a neural network is trained, it is essential to monitor its performance regularly and evaluate its results. This allows for identifying any issues or areas for improvement. Techniques such as cross-validation, confusion matrices, and various evaluation metrics can be used to assess the network's performance and make necessary adjustments. By implementing these optimization techniques, we can significantly enhance the performance of neural networks and achieve better results in various applications. It is important to experiment with different strategies and fine-tune the network to find the optimal configuration for a specific task. 10. Interpreting neural networks. 10.1 Understanding neural network decisions. Artificial neural networks (ANNs) have gained significant popularity in recent years due to their ability to solve complex problems and make accurate predictions. However, one of the challenges with ANNs is their lack of interpretability. Unlike traditional algorithms where the decision-making process is transparent, ANNs often operate as black boxes, making it difficult to understand how they arrive at their decisions. This lack of interpretability has raised concerns in various fields, including healthcare, finance, and law, where the ability to explain and justify decisions is crucial. In this section, we will explore the importance of understanding neural network decisions and discuss various techniques and approaches that can help interpret the decision-making process of ANNs. By gaining insights into how ANNs arrive at their predictions, we can enhance trust, identify biases, and improve the overall transparency and accountability of these powerful models. 10.1.1 The need for interpretability. Interpretability is essential for several reasons. First and foremost, it helps build trust in the predictions made by ANNs. When using ANNs in critical applications such as medical diagnosis or autonomous vehicles, it is crucial to understand why a particular decision was made. This understanding allows domain experts to validate the predictions and identify potential errors or biases. Interpretability also helps identify biases and discrimination that may be present in the training data or the model itself. ANNs learn from large datasets, and if these datasets contain biased information, the model may inadvertently make biased decisions. By interpreting the decision-making process, we can identify and address these biases, ensuring fairness and equality in the predictions. Furthermore, interpretability enables the identification of vulnerabilities and weaknesses in the model. By understanding how the model arrives at its decisions, we can identify scenarios where the model may fail or make incorrect predictions. This knowledge allows us to improve the model's performance and reliability. 10.1.2 Techniques for interpreting neural network decisions. Several techniques have been developed to interpret the decisions made by ANNs. These techniques aim to provide insights into the internal workings of the model and shed light on the factors that influence the predictions. Here are some commonly used techniques. 10.1.2.1 Feature importance. Feature importance techniques aim to identify the input features that have the most significant impact on the model's predictions. By quantifying the importance of each feature, we can understand which factors the model relies on the most. Techniques such as permutation importance, partial dependence plots, and Shapley additive explanations, values are commonly used to determine feature importance. 10.1.2.2 Sensitivity analysis. Sensitivity analysis involves systematically varying the input features and observing the corresponding changes in the model's predictions. By analyzing how the predictions change with different inputs, we can gain insights into the model's sensitivity to specific features. Sensitivity analysis can help identify critical features and understand how they influence the model's decisions. 10.1.2.3 Layer-wise relevance propagation. Layer-wise relevance propagation (LRP) is a technique that aims to attribute the model's predictions to specific input features. LRP assigns relevance scores to each input feature, indicating their contribution to the final prediction. By visualizing these relevance scores, we can understand which features the model focuses on when making decisions. 10.1.2.4 Rule extraction. Rule extraction techniques aim to extract human-readable rules from the trained neural network. These rules provide a simplified representation of the model's decision-making process, making it easier to understand and interpret. Rule extraction techniques often involve converting the neural network into a decision tree or a set of logical rules. 10.1.3 Evaluating neural network interpretability. Evaluating the interpretability of neural networks is essential to ensure the reliability and usefulness of the interpretation techniques. Several metrics and approaches have been proposed to evaluate the interpretability of ANNs. Here are some commonly used evaluation methods. 10.1.3.1 Simplicity. Simplicity refers to the ease of understanding and communicating the interpretation results. A good interpretation technique should provide clear and concise explanations that are easily understandable by domain experts and non-experts alike. The simplicity of the interpretation should also be evaluated in terms of the complexity of the underlying model. 10.1.3.2 Consistency. Consistency refers to the stability and reproducibility of the interpretation results. A reliable interpretation technique should produce consistent results when applied to the same model with different inputs or variations of the training data. Consistency is crucial to ensure that the interpretation is not influenced by random noise or artifacts in the data. 10.1.3.3 Faithfulness. Faithfulness refers to the accuracy and fidelity of the interpretation results. The interpretation should accurately reflect the decision-making process of the neural network. It should capture the important factors and relationships that influence the predictions. Evaluating faithfulness often involves comparing the interpretation results with domain knowledge or expert opinions. 10.1.3.4 Robustness. Robustness refers to the stability of the interpretation results under perturbations or adversarial attacks. A robust interpretation technique should provide consistent and reliable results even when the input data is modified or manipulated. Robustness is crucial to ensure that the interpretation is not easily manipulated or biased. In conclusion, understanding the decisions made by neural networks is crucial for building trust, identifying biases, and improving transparency. Various techniques and evaluation methods can help interpret the decision-making process of ANs. By gaining insights into how ANs arrive at their predictions, we can enhance their reliability, fairness, and overall performance. 10.2 Interpretability techniques for neural networks. Interpretability is a crucial aspect of artificial neural networks, ANs, that allows us to understand and explain the decisions made by these complex models. As ANs become more powerful and widely used in various domains, the need for interpretability techniques becomes increasingly important. In this section, we will explore different methods and approaches to interpret neural networks and gain insights into their decision-making processes. 10.2.1 Feature importance. One way to interpret neural networks is by determining the importance of input features in the decision-making process. Feature importance analysis helps us understand which features have the most significant impact on the network's predictions. There are several techniques available to measure feature importance, such as 10.2.1.1 Gradient-based methods. Gradient-based methods calculate the gradient of the output with respect to the input features. By analyzing the magnitude of the gradients, we can identify which features have the most influence on the network's predictions. For example, the gradient-weighted class activation mapping (GradCam) technique uses the gradients to generate heat maps that highlight the regions of an image that contribute the most to the network's decision. 10.2.1.2 Permutation importance. Permutation importance is a technique that involves randomly permuting the values of a feature and measuring the impact on the model's performance. By comparing the model's performance before and after permuting a feature, we can determine the importance of that feature. This method is particularly useful for models with nonlinear activation functions, such as neural networks. 10.2.2 Layer-wise relevance propagation. Layer-wise relevance propagation (LRP) is a technique used to attribute the network's prediction to individual input features. LRP aims to distribute the relevance of the output back to the input features, providing a clear understanding of which features contribute positively or negatively to the prediction. LRP can be applied to different types of neural networks, including feedforward, recurrent, and convolutional networks. 10.2.3 Rule extraction. Rule extraction techniques aim to extract human-readable rules from trained neural networks. These rules provide a simplified representation of the network's decision-making process, making it easier for humans to understand and interpret. One popular rule extraction method is the sequential covering algorithm, which generates a set of if-then rules based on the network's learned weights and activation functions. 10.2.4 Model visualization. Model visualization techniques help us visualize the internal workings of neural networks. By visualizing the network's architecture, we can gain insights into how information flows through the layers and understand the transformations that occur at each stage. Visualization techniques include network graphs, which illustrate the connections between neurons, and activation maps, which show the activation patterns of individual neurons or layers. 10.2.5 Counterfactual explanations. Counterfactual explanations provide insights into how changing the input features would affect the network's predictions. By generating counterfactual examples, we can understand the decision boundaries of the network and explore different scenarios. For example, in image classification tasks, counterfactual explanations can show how modifying certain pixels would change the predicted class. 10.2.6 Local explanations. Local explanations focus on interpreting the predictions of neural networks on a per-instance basis. Instead of providing a global understanding of the model, local explanations aim to explain individual predictions. Techniques such as LIME, local interpretable model agnostic explanations, generate local explanations by training a simpler, interpretable model on a subset of the data around the instance of interest. 10.2.7 Model distillation. Model distillation is a technique that involves training a smaller, more interpretable model to mimic the behavior of a larger, more complex neural network. By distilling the knowledge from the complex model into a simpler one, we can achieve a more interpretable model without sacrificing performance. This approach is particularly useful when deploying neural networks in resource-constrained environments or when interpretability is a critical requirement. 10.2.8 Ensemble methods. Ensemble methods combine multiple neural networks to improve interpretability and robustness. By training multiple models with different architectures or initializations, we can obtain a consensus decision or measure the uncertainty of the predictions. Ensemble methods, such as bagging and boosting, can provide more reliable interpretations by reducing the bias and variance of individual models. In conclusion, interpretability techniques play a vital role in understanding and explaining the decisions made by artificial neural networks. By employing feature importance analysis, layer-wise relevance propagation, rule extraction, model visualization, counterfactual explanations, local explanations, model distillation, and ensemble methods, we can gain valuable insights into the inner workings of neural networks. These techniques not only enhance our understanding of the models but also help build trust and confidence in their predictions, making them more accessible and usable in real-world applications. 10.3 Explaining neural network predictions. Artificial neural networks (ANNs) have gained significant popularity in recent years due to their ability to make accurate predictions and classifications in various domains. However, one of the challenges with ANNs is their lack of interpretability. Unlike traditional machine learning models, such as decision trees or linear regression, ANNs are often considered black boxes, making it difficult to understand how they arrive at their predictions. This lack of interpretability can be a significant barrier to the adoption of ANNs in critical applications, where understanding the reasoning behind predictions is crucial. In recent years, there has been a growing interest in developing techniques to explain the predictions made by ANNs. These techniques aim to provide insights into the internal workings of the network and shed light on the factors that contribute to its decision-making process. By explaining the predictions, users can gain trust in the model, understand its limitations, and identify potential biases or errors. 10.3.1 Importance of explaining neural network predictions. Explaining neural network predictions is essential for several reasons. Firstly, it helps users understand the factors that influence the model's decision-making process. By providing explanations, users can gain insights into the features or patterns that the network considers important when making predictions. This understanding can be valuable in various domains, such as healthcare, finance, and autonomous systems, where decisions based on neural network predictions can have significant consequences. Secondly, explaining neural network predictions can help identify biases or errors in the model. ANNs are trained on large datasets, and if these datasets contain biases or errors, the network can learn and propagate them. By explaining the predictions, users can identify instances where the model might be making incorrect or biased decisions. This knowledge can then be used to improve the training process, refine the dataset, or introduce fairness measures to mitigate biases. Lastly, explaining neural network predictions can enhance the transparency and accountability of AI systems. As AI systems become more prevalent in society, there is a growing need for transparency and accountability in their decision-making processes. By providing explanations for predictions, AI systems can be held accountable for their actions, and users can have a better understanding of how and why certain decisions are made. 10.3.2 Techniques for explaining neural network predictions. Several techniques have been developed to explain the predictions made by neural networks. These techniques can be broadly categorized into two main approaches: model-agnostic and model-specific explanations. 10.3.2.1 Model-agnostic explanations. Model-agnostic techniques aim to explain the predictions of any black box model, including neural networks. These techniques do not require access to the internal structure or parameters of the network and can be applied to any model without modification. Some popular model-agnostic techniques include LIME, Local Interpretable Model-Agnostic Explanations. LIME generates local explanations by approximating the behavior of the black box model using a simpler interpretable model, such as linear regression or decision trees. It creates perturbations around the instance of interest and observes how the predictions change, providing insights into the features that influence the model's decision. SHAP, Shapley Additive Explanations. SHAP is based on cooperative game theory and assigns a value to each feature based on its contribution to the prediction. It considers all possible combinations of features and calculates the average contribution of each feature across all possible coalitions. This approach provides a unified framework for explaining predictions and can be applied to a wide range of models, including neural networks. 10.3.2.2 Model-specific explanations. Model-specific techniques aim to explain the predictions of a specific type of model, such as neural networks. These techniques leverage the internal structure and parameters of the network to provide explanations. Some popular model-specific techniques include gradient-based methods. Gradient-based methods analyze the gradients of the network with respect to the input features to understand their importance. For example, gradient-weighted class activation mapping (GradCam) highlights the regions of an input image that contribute most to the prediction by visualizing the gradients of the predicted class with respect to the input image. Layer-wise relevance propagation (LRP). LRP assigns relevance scores to each neuron in the network by backpropagating the prediction through the network. It aims to distribute the prediction score to the input features based on their contribution, providing insights into the features that are most relevant to the prediction. 10.3.3 Challenges in explaining neural network predictions. While significant progress has been made in explaining neural network predictions, several challenges still exist. Some of the key challenges include complexity of neural networks. Neural networks can be highly complex, with millions of parameters and multiple layers. Understanding the internal workings of such networks and providing meaningful explanations can be challenging. Trade-off between accuracy and interpretability. There is often a trade-off between the accuracy of a neural network and its interpretability. Techniques that provide high interpretability may sacrifice some accuracy, while highly accurate models may be less interpretable. Striking the right balance between accuracy and interpretability is a challenge. Domain-specific interpretability. Different domains may require different types of explanations. For example, in healthcare, explanations may need to be understandable to medical professionals, while in finance, they may need to be interpretable to regulators. Developing domain-specific interpretability techniques that cater to the specific needs of different domains is a challenge. 10.3.4 Evaluating neural network interpretability. Evaluating the interpretability of neural network explanations is crucial to ensure their effectiveness and reliability. Several metrics and evaluation frameworks have been proposed to assess the quality of explanations. Some common evaluation criteria include fidelity. Fidelity measures how well the explanation approximates the behavior of the black box model. It assesses whether the explanation accurately reflects the factors that influence the model's predictions. Sufficiency. Sufficiency evaluates whether the explanation provides enough information to understand the model's decision-making process. It assesses whether the explanation includes all the relevant factors and features that contribute to the prediction. Consistency. Consistency measures the stability of the explanation across different instances or perturbations. It assesses whether the explanation remains consistent when the input is slightly modified or perturbed. Human comprehensibility. Human comprehensibility evaluates how well humans can understand and interpret the explanation. It assesses whether the explanation is presented in a clear and understandable manner. Evaluating the interpretability of neural network explanations is an ongoing research area, and developing robust evaluation frameworks is essential to ensure the reliability and usefulness of the explanations. In conclusion, explaining neural network predictions is crucial for understanding the decision-making process, identifying biases, and enhancing the transparency and accountability of AI systems. Model-agnostic and model-specific techniques have been developed to provide explanations for neural network predictions. However, challenges such as the complexity of neural networks and the trade-off between accuracy and interpretability still exist. Evaluating the interpretability of explanations is essential to ensure their effectiveness and reliability. As research in this field continues to advance, we can expect further improvements in the interpretability of neural network predictions, making them more accessible and trustworthy in various domains. 10.4 Evaluating neural network interpretability. As artificial neural networks become more complex and powerful, the need for interpretability and understanding of their decision-making processes becomes increasingly important. In this section, we will explore various methods and metrics for evaluating the interpretability of neural networks. 10.4.1 Quantitative metrics for interpretability. Quantitative metrics provide a systematic way to measure the interpretability of neural networks. These metrics aim to capture the degree to which a neural network's decisions can be understood and explained. Here are some commonly used quantitative metrics. 10.4.1.1 Simplicity. Simplicity measures the complexity of a neural network's structure and parameters. A simpler network is often easier to interpret as it has fewer hidden layers, nodes, and connections. Metrics such as the number of parameters, depth of the network, and sparsity can be used to quantify simplicity. 10.4.1.2 Feature importance. Feature importance metrics assess the contribution of each input feature to the network's decision-making process. These metrics help identify which features have the most significant impact on the network's predictions. Techniques such as gradient-based methods, permutation importance, and SHAP values can be used to calculate feature importance. 10.4.1.3 Sensitivity analysis. Sensitivity analysis evaluates how changes in input features affect the network's output. By systematically varying the values of input features and observing the corresponding changes in predictions, we can gain insights into the network's sensitivity to different inputs. Sensitivity analysis can be performed using techniques like input perturbation, partial dependence plots, and saliency maps. 10.4.1.4 Model confidence. Model confidence metrics assess the certainty or confidence of the network's predictions. Higher confidence indicates that the network's decisions are more reliable and easier to interpret. Metrics such as prediction probabilities, confidence intervals, and calibration curves can be used to measure model confidence. 10.4.2 Qualitative evaluation of interpretability. While quantitative metrics provide a structured approach to evaluating interpretability, qualitative evaluation methods offer a more subjective assessment. These methods involve human judgment and expert analysis to assess the interpretability of neural networks. Here are some common qualitative evaluation techniques. 10.4.2.1 Expert review. Expert review involves domain experts examining the network's structure, parameters, and decision-making processes. These experts can provide valuable insights into the interpretability of the network based on their knowledge and expertise in the field. Expert review can help identify potential biases, errors, or limitations in the network's interpretability. 10.4.2.2 User feedback. User feedback involves gathering opinions and feedback from end users or stakeholders who interact with the network's predictions. This feedback can provide valuable insights into the understandability and usefulness of the network's decisions. User feedback can be collected through surveys, interviews, or usability testing. 10.4.2.3 Case studies. Case studies involve analyzing real-world examples or scenarios where the network's decisions have been applied. By examining the network's predictions in specific contexts, we can assess the interpretability and effectiveness of the network's decision-making process. Case studies can provide valuable insights into the practical implications and limitations of the network's interpretability. 10.4.3 Challenges in evaluating interpretability. Evaluating the interpretability of neural networks is not without its challenges. Here are some common challenges that researchers and practitioners face. 10.4.3.1 Lack of ground truth. Interpretability is often subjective and context-dependent. There is no definitive, ground truth, measure of interpretability, making it challenging to establish a universal evaluation framework. Different stakeholders may have different interpretations and requirements for interpretability. 10.4.3.2 Trade-off with performance. Increasing the interpretability of a neural network may come at the cost of performance. Simplifying the network structure or adding interpretability constraints can lead to a decrease in accuracy or predictive power. Balancing interpretability and performance is a crucial challenge in evaluating neural network interpretability. 10.4.3.3 Complexity of neural networks. Neural networks can be highly complex, with millions of parameters and intricate architectures. Understanding and interpreting such complex networks can be challenging, even with the help of quantitative metrics and qualitative evaluation methods. Simplifying the interpretation of complex networks without losing important information is a significant challenge. 10.4.4 Future directions in evaluating interpretability. The field of evaluating neural network interpretability is still evolving, and researchers are actively exploring new methods and techniques. Here are some potential future directions. 10.4.4.1 Explainable AI benchmarks. Developing standardized benchmarks and evaluation frameworks for interpretability can help compare different models and techniques. These benchmarks can include datasets, evaluation metrics, and reference models to facilitate fair and consistent evaluation of interpretability. 10.4.4.2 Human-centered evaluation. Incorporating human-centered evaluation methods can provide a more holistic understanding of interpretability. This can involve user studies, cognitive psychology experiments, and qualitative analysis of human interpretations of neural network decisions. 10.4.4.3 Interdisciplinary collaboration. Collaboration between researchers from different disciplines, such as computer science, cognitive science, and ethics, can enrich the evaluation of interpretability. By combining expertise from various fields, we can develop more comprehensive evaluation frameworks and address the ethical and societal implications of interpretability. In conclusion, evaluating the interpretability of neural networks is a complex and multifaceted task. It requires a combination of quantitative metrics and qualitative evaluation methods to assess the understandability, transparency, and reliability of neural network decisions. As the field progresses, developing standardized evaluation frameworks and incorporating human-centered approaches will be crucial in advancing the interpretability of neural networks. 11. Ethical considerations in neural networks. 11.1 Bias and fairness in neural networks. Artificial neural networks have gained significant attention and popularity in recent years due to their ability to learn and make predictions from complex data. However, like any other technology, neural networks are not immune to biases and fairness issues. In this section, we will explore the concept of bias in neural networks, its impact on fairness, and the challenges associated with addressing these ethical considerations. 11.1.1 Understanding bias in neural networks. Bias in neural networks refers to the systematic favoritism or prejudice towards certain groups or individuals in the data used for training. This bias can arise from various sources, including biased training data, biased feature selection, or biased assumptions made during the model development process. It is important to note that bias in neural networks is not intentional but rather a reflection of the biases present in the data used for training. One common example of bias in neural networks is the underrepresentation or misrepresentation of certain demographic groups. For instance, if a facial recognition system is trained predominantly on data from a specific racial group, it may perform poorly when attempting to recognize faces from other racial groups. This can lead to unfair outcomes and discrimination against individuals from underrepresented groups. 11.1.2 The impact of bias on fairness. The presence of bias in neural networks can have significant implications for fairness. When biased models are deployed in real-world applications, they can perpetuate and amplify existing societal biases and inequalities. For example, biased hiring algorithms can result in discriminatory practices by favoring certain demographic groups over others. Similarly, biased loan approval systems can disproportionately deny loans to individuals from marginalized communities. Fairness in neural networks refers to the absence of discriminatory outcomes and the equitable treatment of all individuals, regardless of their demographic characteristics. Achieving fairness requires addressing bias and ensuring that the predictions and decisions made by neural networks are not influenced by factors such as race, gender, or socioeconomic status. 11.1.3 Challenges in addressing bias and fairness. Addressing bias and fairness in neural networks is a complex and multifaceted challenge. There are several key challenges that need to be overcome to ensure that neural networks are fair and unbiased. 11.1.3.1 Data bias. One of the primary challenges is the presence of bias in the training data itself. If the training data is biased, the neural network will learn and perpetuate those biases. It is crucial to carefully curate and preprocess the training data to minimize bias and ensure representativeness across different demographic groups. Additionally, techniques such as data augmentation and oversampling can be employed to increase the diversity of the training data. 11.1.3.2 Algorithmic bias. Another challenge is algorithmic bias, which refers to biases that are introduced during the model development process. Biases can arise from the choice of features, the design of the neural network architecture, or the selection of the loss function. It is essential to critically examine and evaluate the design choices made during the development of neural networks to identify and mitigate algorithmic biases. 11.1.3.3 Evaluation metrics. Measuring and evaluating the fairness of neural networks is a non-trivial task. Traditional evaluation metrics such as accuracy may not capture the discriminatory impact of biased models. New metrics and evaluation techniques need to be developed to assess the fairness of neural networks accurately. These metrics should consider the differential impact of the model's predictions on different demographic groups and ensure equitable outcomes. 11.1.3.4 Interpretability and transparency. Interpretability and transparency are crucial for understanding the decision-making process of neural networks. It is essential to develop techniques that can explain the factors influencing the predictions made by neural networks. This can help identify and address biases in the decision-making process and provide insights into the fairness of the model. 11.1.4 Mitigating bias and ensuring fairness. Addressing bias and ensuring fairness in neural networks requires a combination of technical, ethical, and regulatory approaches. Here are some strategies that can be employed to mitigate bias and promote fairness. 11.1.4.1 Diverse and representative training data. Ensuring that the training data used for neural networks is diverse and representative of the population is crucial. This can be achieved by collecting data from a wide range of sources and demographic groups. Additionally, data augmentation techniques can be used to increase the diversity of the training data. 11.1.4.2 Regular monitoring and evaluation. Regular monitoring and evaluation of neural networks are essential to identify and address biases. This can involve analyzing the predictions made by the model and assessing their impact on different demographic groups. If biases are detected, appropriate corrective measures should be taken to mitigate them. 11.1.4.3 Algorithmic fairness techniques. Various algorithmic fairness techniques can be employed to mitigate bias in neural networks. These techniques include pre-processing the data to remove bias, modifying the training process to account for fairness constraints, and post-processing the model's predictions to ensure equitable outcomes. 11.1.4.4 Ethical guidelines and regulations. The development and deployment of neural networks should be guided by ethical guidelines and regulations. These guidelines can provide a framework for addressing bias and ensuring fairness. Regulatory bodies can play a crucial role in enforcing these guidelines and holding organizations accountable for the ethical use of neural networks. In conclusion, bias and fairness are critical ethical considerations in the development and deployment of neural networks. Addressing bias and ensuring fairness requires a combination of technical, ethical, and regulatory approaches. By actively working towards mitigating bias and promoting fairness, we can harness the full potential of neural networks while minimizing the negative societal impact. 11.2 Privacy and security concerns. As artificial neural networks (ANs) continue to advance and become more prevalent in various industries and applications, it is crucial to address the privacy and security concerns associated with these powerful systems. While ANs offer numerous benefits, such as improved decision-making and automation, they also raise significant ethical considerations that must be carefully managed. 11.2.1 Data privacy. One of the primary concerns surrounding ANs is the protection of data privacy. ANs rely on vast amounts of data to train and make accurate predictions. However, this data often contains sensitive information about individuals, such as personal details, financial records, or medical history. Therefore, it is essential to ensure that this data is handled securely and that privacy regulations are strictly followed. To address data privacy concerns, organizations must implement robust data protection measures. This includes encrypting sensitive data, implementing access controls, and anonymizing or de-identifying data whenever possible. Additionally, organizations should establish clear policies and procedures for data handling, including obtaining informed consent from individuals and ensuring compliance with relevant privacy laws and regulations. 11.2.2 Data security. In addition to data privacy, data security is another critical aspect when it comes to ANs. As these networks become more complex and interconnected, they become vulnerable to various security threats. Malicious actors may attempt to gain unauthorized access to the network, manipulate the data, or launch attacks to compromise the integrity and availability of the system. To mitigate these risks, organizations must implement robust security measures. This includes implementing secure authentication and access controls to prevent unauthorized access to the network and its data. Regular security audits and vulnerability assessments should be conducted to identify and address any potential weaknesses. Additionally, organizations should stay updated with the latest security patches and employ encryption techniques to protect data both at rest and in transit. 11.2.3 Adversarial attacks. Adversarial attacks pose a unique challenge to the security of ANS. These attacks involve intentionally manipulating the input data to deceive the network and produce incorrect or malicious outputs. Adversarial attacks can have severe consequences, especially in critical applications such as autonomous vehicles or healthcare systems. To defend against adversarial attacks, researchers are developing robust defense mechanisms. These mechanisms aim to detect and mitigate the impact of adversarial inputs by enhancing the network's resilience and robustness. Techniques such as adversarial training, input sanitization, and anomaly detection can help identify and mitigate the effects of adversarial attacks. 11.2.4 Model inversion and membership inference attacks. Model inversion and membership inference attacks are privacy-related concerns that exploit the information leakage from trained ANS. In model inversion attacks, an adversary attempts to reconstruct sensitive training data or extract information about specific individuals from the trained model. Membership inference attacks, on the other hand, aim to determine whether a particular individual's data was used during the training process. To protect against these attacks, organizations can employ techniques such as differential privacy, which adds noise to the training data to prevent the reconstruction of sensitive information. Additionally, organizations should carefully consider the data they use for training and implement strict access controls to limit the exposure of sensitive information. 11.2.5 Regulatory compliance. Given the potential risks associated with ANS, regulatory compliance becomes crucial. Organizations must ensure that they comply with relevant privacy and security regulations, such as the General Data Protection Regulation (GDPR) in the European Union or the Health Insurance Portability and Accountability Act (HIPAA) in the United States. Compliance involves implementing appropriate technical and organizational measures to protect data privacy and security. This includes conducting privacy impact assessments, appointing data protection officers, and establishing clear policies and procedures for data handling. Organizations should also provide individuals with transparency and control over their data, including the ability to access, rectify, or delete their information. 11.2.6 Ethical considerations. Privacy and security concerns in ANS also raise broader ethical considerations. Organizations must ensure that the use of ANS aligns with ethical principles and values. This includes promoting fairness and avoiding bias in decision-making, ensuring transparency and explainability of the network's predictions, and considering the potential societal impact of deploying ANS in various domains. To address these ethical considerations, organizations should establish ethical guidelines and frameworks for the development and deployment of ANS. This includes involving multidisciplinary teams, including ethicists and domain experts, in the design and decision-making processes. Regular ethical audits and assessments should be conducted to evaluate the impact of ANS on individuals and society as a whole. In conclusion, while artificial neural networks offer tremendous potential, it is crucial to address the privacy and security concerns associated with their use. Organizations must prioritize data privacy and security, implement robust security measures, and comply with relevant regulations. Additionally, ethical considerations should guide the development and deployment of ANS to ensure fairness, transparency, and accountability. By addressing these concerns, we can harness the power of ANS while safeguarding individuals' privacy and maintaining trust in these transformative technologies. 11.3 Transparency and accountability. Transparency and accountability are crucial aspects when it comes to the deployment and use of artificial neural networks (ANS). As ANS become more prevalent in various domains, it is essential to ensure that these systems are transparent in their decision-making processes and accountable for their actions. This chapter explores the importance of transparency and accountability in ANS, the challenges associated with achieving them, and potential solutions to address these issues. 11.3.1 The need for transparency. Transparency in ANS refers to the ability to understand and explain the reasoning behind the system's decisions. As ANS are often considered black boxes due to their complex internal workings, it can be challenging to interpret how they arrive at specific outcomes. This lack of transparency raises concerns about the fairness, bias, and potential errors in the decision-making process. In many real-world applications, such as healthcare, finance, and criminal justice, the decisions made by ANS can have significant consequences on individuals' lives. Therefore, it is crucial to ensure that these systems are transparent, allowing users and stakeholders to understand the factors influencing the decisions and identify any potential biases or errors. 11.3.2 Challenges in achieving transparency. Achieving transparency in ANS is not a straightforward task due to several challenges. Some of the key challenges include 11.3.2.1 Complexity of neural networks. Neural networks can be highly complex, with numerous interconnected layers and thousands or even millions of parameters. Understanding the inner workings of such complex systems can be challenging, making it difficult to explain their decisions in a human-readable manner. 11.3.2.2 Lack of interpretability. Interpretability refers to the ability to understand and explain the relationship between the input features and the output predictions of an AN. While simpler models like linear regression are highly interpretable, ANs often lack interpretability due to their nonlinear nature and complex interactions between neurons. This lack of interpretability hinders transparency and makes it challenging to explain the reasoning behind the system's decisions. 11.3.2.3 Data privacy concerns. Transparency often requires access to the underlying data used to train the AN. However, in many cases, this data may contain sensitive or private information. Striking a balance between transparency and data privacy is a significant challenge, as revealing sensitive information can lead to privacy breaches and potential misuse of personal data. 11.3.3 Approaches to enhance transparency. While achieving complete transparency in ANs may be challenging, several approaches can enhance transparency and provide insights into the decision-making process. Some of these approaches include 11.3.3.1 Explainable AI (XAI) techniques. Explainable AI (XAI) techniques aim to make the decision-making process of ANs more transparent and interpretable. These techniques provide insights into how the network arrived at a particular decision by generating explanations or visualizations of the internal workings of the network. XAI techniques include methods like feature importance analysis, saliency maps, and rule extraction algorithms. 11.3.3.2 Model documentation and reporting. Documenting and reporting the details of the AN model, including the architecture, hyperparameters, and training data, can enhance transparency. This documentation allows users and stakeholders to understand the model's limitations, potential biases, and the factors influencing its decisions. 11.3.3.3 Algorithmic auditing. Algorithmic auditing involves conducting independent assessments of the AN's decision-making process to identify potential biases, errors, or unfairness. These audits can help ensure that the system is accountable for its actions and provide insights into any ethical or legal concerns associated with its use. 11.3.4 Ensuring accountability. Accountability in ANs refers to the responsibility and liability for the system's actions. It involves holding the developers, operators, and users of ANs accountable for the decisions made by these systems. Ensuring accountability is essential to prevent misuse, bias, or unfairness in the deployment and use of ANs. 11.3.4.1 Ethical guidelines and standards. Developing and adhering to ethical guidelines and standards can help ensure accountability in the use of ANs. These guidelines should address issues such as fairness, bias, privacy, and transparency. They can provide a framework for developers and users to follow, promoting responsible and accountable use of ANs. 11.3.4.2 Regulatory frameworks. Regulatory frameworks can play a crucial role in ensuring accountability in the deployment and use of ANs. Governments and regulatory bodies can establish guidelines, laws, and regulations that govern the use of ANs in specific domains. These frameworks can include requirements for transparency, fairness, and accountability, ensuring that ANs are used responsibly and ethically. 11.3.4.3 Independent oversight and auditing. Independent oversight and auditing can help ensure accountability by providing external scrutiny of the decisions made by ANs. Independent organizations or regulatory bodies can conduct audits to assess the fairness, transparency, and ethical implications of the system's decisions. These audits can help identify and address any biases, errors, or ethical concerns associated with the use of ANs. Conclusion. Transparency and accountability are critical considerations in the deployment and use of artificial neural networks. While achieving complete transparency may be challenging due to the complexity of ANs, approaches like explainable AI techniques, model documentation, and algorithmic auditing can enhance transparency and provide insights into the decision-making process. Ensuring accountability requires the development of ethical guidelines, regulatory frameworks, and independent oversight to hold developers, operators, and users accountable for the actions of ANs. By addressing these challenges and implementing appropriate measures, we can promote responsible and ethical use of ANs in various domains. 11.4 Addressing ethical issues in neural networks. As artificial neural networks continue to advance and become more integrated into various aspects of our lives, it is crucial to address the ethical issues that arise from their use. While neural networks have the potential to revolutionize industries and improve our daily lives, they also bring about concerns related to bias, privacy, transparency, and accountability. In this section, we will explore these ethical considerations and discuss potential solutions to address them. 11.4.1 Bias and fairness in neural networks. One of the most significant ethical concerns in neural networks is the issue of bias and fairness. Neural networks learn from large datasets, and if these datasets contain biased information, the resulting models can perpetuate and amplify those biases. This can lead to unfair outcomes and discrimination in various domains, such as hiring processes, loan approvals, and criminal justice systems. To address bias and fairness issues, it is crucial to ensure that the training data used for neural networks is diverse, representative, and free from biases. Data collection processes should be carefully designed to avoid sampling biases and to include a wide range of demographics and perspectives. Additionally, techniques such as data augmentation and oversampling can be used to balance the representation of different groups in the dataset. Another approach to address bias is through the use of fairness metrics and algorithms. These metrics can be incorporated into the training process to explicitly optimize for fairness and mitigate the impact of biased data. By considering fairness as a core objective during model development, we can reduce the potential for discriminatory outcomes. 11.4.2 Privacy and security concerns. Neural networks often require access to large amounts of personal data to train and make accurate predictions. This raises significant privacy concerns, as the misuse or mishandling of this data can lead to breaches of personal information and invasions of privacy. Additionally, there is a risk of adversarial attacks, where malicious actors manipulate the input data to deceive the neural network or extract sensitive information. To address privacy concerns, it is essential to implement robust data protection measures. This includes anonymizing and encrypting personal data, implementing strict access controls, and ensuring compliance with relevant privacy regulations. Furthermore, techniques such as federated learning, where models are trained on decentralized data, can help preserve privacy by keeping sensitive data on local devices. To mitigate the risk of adversarial attacks, researchers are developing techniques to make neural networks more robust against such attacks. Adversarial training, where models are trained with adversarial examples, can help improve their resilience. Additionally, ongoing research in secure and private machine learning aims to develop methods that protect both the model and the data during training and inference. 11.4.3 Transparency and accountability. Neural networks are often considered black boxes, meaning that their decision-making processes are not easily interpretable or explainable. This lack of transparency raises concerns about accountability, as it becomes challenging to understand how and why a neural network arrived at a particular decision. This is particularly problematic in critical domains such as healthcare, finance, and autonomous vehicles, where the consequences of incorrect or biased decisions can be severe. To address the transparency and accountability issues, researchers are developing techniques for interpreting and explaining neural network decisions. Methods such as feature importance analysis, saliency maps, and attention mechanisms can provide insights into the factors influencing a neural network's predictions. By understanding the decision-making process, we can identify potential biases, errors, or limitations and take appropriate actions. Furthermore, efforts are being made to develop standards and regulations that promote transparency and accountability in the deployment of neural networks. These include requirements for documentation, auditing, and third-party validation of models. By establishing clear guidelines and standards, we can ensure that the development and deployment of neural networks are conducted in an accountable and transparent manner. 11.4.4 Addressing ethical issues in neural networks. Addressing ethical issues in neural networks requires a multifaceted approach involving various stakeholders, including researchers, developers, policymakers, and the general public. Collaboration and open dialogue are essential to ensure that the benefits of neural networks are maximized while minimizing the potential harms. To begin with, organizations and researchers should adopt ethical guidelines and frameworks that prioritize fairness, privacy, transparency, and accountability. These guidelines should be integrated into the entire lifecycle of neural network development, from data collection and model training to deployment and ongoing monitoring. Education and awareness programs are also crucial to ensure that individuals understand the ethical implications of neural networks. By promoting digital literacy and providing resources for responsible AI use, we can empower individuals to make informed decisions and hold organizations accountable for their actions. Furthermore, policymakers play a vital role in shaping the ethical landscape of neural networks. They should develop regulations and policies that address the ethical concerns associated with neural networks, while also fostering innovation and technological advancement. These policies should strike a balance between protecting individual rights and promoting the responsible use of neural networks. Lastly, it is essential for organizations to establish internal mechanisms for ethical review and oversight. This includes conducting regular audits of models, ensuring diverse representation in decision-making processes, and providing channels for reporting and addressing ethical concerns. By taking a proactive and collaborative approach, we can navigate the ethical challenges posed by neural networks and harness their potential for positive impact. It is crucial to prioritize the ethical considerations and ensure that the development and deployment of neural networks align with our societal values and aspirations. 12. The future of neural networks. 12.1 Emerging trends in neural networks. Artificial neural networks (ANNs) have come a long way since their inception. Over the years, they have revolutionized various fields, including computer vision, natural language processing, and robotics. As technology continues to advance, new trends are emerging in the field of neural networks, paving the way for exciting developments and applications. In this section, we will explore some of the emerging trends in neural networks and their potential impact on the future. 12.1.1 Deep learning. Deep learning is a subfield of machine learning that focuses on training neural networks with multiple layers. Traditional neural networks were limited in their ability to learn complex patterns due to their shallow architecture. However, deep learning has overcome this limitation by introducing deep neural networks with many hidden layers. Deep learning has gained significant attention in recent years due to its remarkable performance in various tasks, such as image recognition, speech recognition, and natural language processing. The ability of deep neural networks to automatically learn hierarchical representations from raw data has led to breakthroughs in these domains. With the increasing availability of large datasets and powerful computing resources, deep learning has become more accessible and scalable. Researchers are continuously exploring new architectures, optimization techniques, and regularization methods to improve the performance and efficiency of deep neural networks. As deep learning continues to evolve, it holds great promise for solving complex real-world problems. 12.1.2 Explainable AI. As neural networks become more powerful and complex, there is a growing need for transparency and interpretability. Explainable AI (XAI) aims to address this challenge by providing insights into how neural networks make decisions. XAI techniques enable users to understand the reasoning behind a neural network's predictions, making it easier to trust and validate the model's outputs. Researchers are developing various methods to interpret and explain the inner workings of neural networks. These techniques range from visualizing the learned features and attention mechanisms to generating human-readable explanations for individual predictions. By providing interpretable explanations, XAI can help identify biases, detect errors, and improve the overall transparency of neural network models. 12.1.3 Transfer learning and few-shot learning. Transfer learning is a technique that allows neural networks to leverage knowledge learned from one task to improve performance on another related task. Instead of training a neural network from scratch for each new task, transfer learning enables the model to transfer its learned representations and knowledge to new domains. Transfer learning has proven to be highly effective, especially in scenarios where labeled data is scarce. By leveraging pre-trained models on large datasets, neural networks can quickly adapt to new tasks with limited labeled data. This approach has been particularly successful in computer vision tasks, where pre-trained models trained on massive image datasets, such as ImageNet, have been used as a starting point for various applications. In addition to transfer learning, few-shot learning is another emerging trend that aims to train neural networks with very limited labeled data. Few-shot learning techniques enable models to learn from a small number of examples, mimicking the way humans can quickly generalize and learn new concepts with minimal exposure. This area of research holds great potential for applications where acquiring large amounts of labeled data is challenging or expensive. 12.1.4 Reinforcement learning and neural networks. Reinforcement learning (RL) is a branch of machine learning that focuses on training agents to make sequential decisions in an environment to maximize a reward signal. Neural networks have played a crucial role in RL, enabling agents to learn complex policies and value functions. Recent advancements in RL, such as the development of deep Q networks (DQNs), have led to significant breakthroughs in areas like game playing and robotics. DQNs combine deep neural networks with Q-learning, a popular RL algorithm, to learn optimal policies directly from raw sensory inputs. The integration of neural networks and RL has opened up new possibilities for solving complex problems that were previously considered challenging or infeasible. Researchers are exploring various techniques to improve the stability, sample efficiency, and generalization capabilities of RL algorithms using neural networks. 12.1.5 Neuroevolution and genetic algorithms. Neuroevolution is a field that combines neural networks with evolutionary algorithms to evolve optimal neural network architectures and parameters. Genetic algorithms, a popular evolutionary technique, are used to evolve populations of neural networks through processes like mutation, crossover, and selection. Neuroevolution has gained attention as a promising alternative to traditional gradient-based optimization methods. It offers advantages in scenarios where the search space is large, the objective function is non-differentiable, or the training data is limited. By leveraging the principles of evolution, neuroevolution can discover novel neural network architectures and optimize them for specific tasks. Researchers are exploring various neuroevolution techniques, such as novelty search, coevolution, and multi-objective optimization, to improve the efficiency and effectiveness of evolving neural networks. Neuroevolution holds great potential for solving complex problems and discovering innovative neural network architectures. 12.1.6 Quantum neural networks. Quantum computing is an emerging field that leverages the principles of quantum mechanics to perform computations that are infeasible for classical computers. Quantum neural networks (QNNs) combine the power of quantum computing with the flexibility and expressiveness of neural networks. QNNs have the potential to solve complex optimization problems, simulate quantum systems, and enhance machine learning algorithms. They can leverage quantum entanglement and superposition to process and represent information in ways that classical neural networks cannot. Although quantum computing is still in its early stages, researchers are actively exploring the intersection of quantum computing and neural networks. The development of quantum hardware and algorithms specifically designed for neural networks holds great promise for solving computationally intensive tasks and unlocking new capabilities in machine learning. In conclusion, the field of neural networks is constantly evolving, driven by emerging trends and advancements in technology. Deep learning, explainable AI, transfer learning, reinforcement learning, neuroevolution, and quantum neural networks are just a few of the exciting areas that are shaping the future of neural networks. As researchers continue to push the boundaries of what is possible, we can expect neural networks to play an increasingly significant role in solving complex real-world problems and driving innovation across various industries. 12.2 Advancements in hardware for neural networks. As the field of artificial neural networks continues to evolve and expand, advancements in hardware play a crucial role in enabling the development and deployment of increasingly complex and powerful neural networks. The demand for faster and more efficient hardware solutions has driven significant progress in the design and implementation of specialized hardware architectures specifically tailored for neural network computations. In this section, we will explore some of the key advancements in hardware for neural networks and their implications for the future of this field. 12.2.1 Specialized neural network processors. One of the most significant advancements in hardware for neural networks is the development of specialized processors designed to accelerate neural network computations. These processors, often referred to as neural processing units (NPUs) or tensor processing units (TPUs), are specifically optimized for the parallel and computationally intensive nature of neural network operations. Unlike traditional central processing units (CPUs) or graphics processing units (GPUs), NPUs and TPUs are designed to perform matrix multiplications and other neural network operations with exceptional speed and efficiency. These specialized processors leverage parallel processing techniques and hardware optimizations to accelerate the training and inference processes of neural networks. By offloading the computational workload from general-purpose processors, NPUs and TPUs can significantly reduce the time required for training complex neural networks. This advancement in hardware has opened up new possibilities for training larger and more sophisticated models, enabling breakthroughs in various domains such as computer vision, natural language processing, and reinforcement learning. 12.2.2 Hardware acceleration techniques. In addition to specialized neural network processors, hardware acceleration techniques have also played a crucial role in advancing the capabilities of neural networks. These techniques aim to optimize the performance of neural network computations by leveraging various hardware-level optimizations. One such technique is the use of field programmable gate arrays (FPGAs), which allow for the customization of hardware circuits to match the specific requirements of neural network operations. FPGAs offer the flexibility to implement custom hardware architectures that can be tailored to the specific neural network model being used. This customization enables the execution of neural network computations with higher efficiency and lower power consumption compared to traditional processors. Furthermore, FPGAs can be reprogrammed to adapt to different neural network architectures, making them a versatile and scalable hardware solution for neural network acceleration. Another hardware acceleration technique gaining traction is the use of application-specific integrated circuits, ASICs, designed specifically for neural network computations. ASICs offer even greater performance and power efficiency compared to FPGAs by implementing dedicated circuits optimized for neural network operations. These specialized chips can be integrated into various devices, ranging from edge devices like smartphones and IoT devices to data centers, enabling efficient and real-time inference of neural network models. 12.2.3 Neuromorphic computing. Neuromorphic computing is an emerging field that aims to mimic the structure and functionality of the human brain in hardware. Unlike traditional digital computing, which relies on binary logic and sequential processing, neuromorphic computing architectures are designed to emulate the parallel and distributed nature of neural networks. These architectures, often referred to as neuromorphic chips, are inspired by the biological neurons and synapses found in the human brain. Neuromorphic chips leverage analog circuits and specialized hardware components to perform neural network computations in a highly efficient and parallel manner. By mimicking the brain's neural connections and synaptic plasticity, these chips can potentially achieve higher computational efficiency and energy savings compared to traditional digital processors. Neuromorphic computing holds great promise for the development of intelligent systems that can perform complex cognitive tasks with minimal power consumption. 12.2.4 Quantum computing and neural networks. Quantum computing, a rapidly advancing field, has the potential to revolutionize the capabilities of neural networks. Unlike classical computers that use bits to represent information, quantum computers use quantum bits or qubits, which can exist in multiple states simultaneously. This property of superposition allows quantum computers to perform computations in parallel, potentially enabling significant speedups for certain types of neural network operations. Quantum neural networks, also known as quantum machine learning, leverage the power of quantum computing to enhance the training and inference processes of neural networks. These networks can exploit quantum algorithms and quantum-inspired optimization techniques to solve complex optimization problems more efficiently. While quantum computing is still in its early stages, ongoing research and development in this field hold the promise of unlocking new frontiers in neural network capabilities. 12.2.5 Future directions and challenges. The advancements in hardware for neural networks discussed in this section have paved the way for the development of increasingly powerful and efficient neural network models. However, several challenges and opportunities lie ahead in this rapidly evolving field. One of the key challenges is the need for hardware that can handle the growing complexity and size of neural network models. As neural networks continue to scale, hardware architectures must be designed to accommodate the increasing computational requirements and memory demands. Another challenge is the integration of hardware advancements with software frameworks and tools. To fully leverage the capabilities of specialized hardware, software frameworks need to be developed or adapted to effectively utilize these hardware accelerators. This integration will enable seamless deployment and efficient utilization of neural network models across a wide range of applications and devices. Furthermore, the ethical implications of advancements in hardware for neural networks must be carefully considered. As neural networks become more powerful and pervasive, ensuring fairness, transparency, and accountability in their deployment becomes crucial. Addressing issues such as bias, privacy, and security will be essential to build trust in neural network technologies and ensure their responsible and ethical use. In conclusion, advancements in hardware for neural networks have played a pivotal role in driving the progress and widespread adoption of this field. Specialized neural network processors, hardware acceleration techniques, neuromorphic computing, and quantum computing are all contributing to the development of more efficient and powerful neural network models. As hardware continues to evolve, the future of neural networks holds immense potential for solving complex problems and transforming various industries. However, addressing the challenges and ethical considerations associated with these advancements will be crucial to ensure the responsible and beneficial integration of neural networks into society. 12.3 Challenges and Opportunities. Artificial neural networks have made significant advancements in recent years, revolutionizing various industries and fields. However, along with these advancements come a set of challenges and opportunities that need to be addressed to fully harness the potential of neural networks. In this section, we will explore some of the key challenges and opportunities that lie ahead in the future of neural networks. 12.3.1 Scalability and Complexity. One of the major challenges in the future of neural networks is scalability and complexity. As neural networks become more powerful and capable of handling larger datasets, the complexity of the models also increases. This complexity poses challenges in terms of training time, computational resources, and memory requirements. Developing efficient algorithms and architectures that can handle this complexity will be crucial for the future of neural networks. 12.3.2 Interpretability and Explainability. Another challenge in the field of neural networks is the lack of interpretability and explainability. Neural networks are often referred to as black boxes because it is difficult to understand how they arrive at their decisions. This lack of interpretability raises concerns in critical applications such as healthcare and finance, where the ability to explain the reasoning behind a decision is crucial. Developing techniques and methods to interpret and explain the decisions made by neural networks will be essential for their widespread adoption in these domains. 12.3.3 Data Privacy and Security. With the increasing use of neural networks in various applications, data privacy and security have become major concerns. Neural networks require large amounts of data to train effectively, and this data often contains sensitive information. Ensuring the privacy and security of this data is of utmost importance. Techniques such as federated learning, which allows training models on decentralized data without sharing the raw data, can help address these concerns. Additionally, developing robust defenses against adversarial attacks and ensuring the integrity of neural networks will be crucial for their future success. 12.3.4 Generalization and Transfer Learning. Neural networks have shown remarkable performance in specific tasks and domains. However, achieving generalization and transfer learning across different tasks and domains remains a challenge. Neural networks often struggle to generalize their knowledge to unseen data or adapt to new tasks without extensive retraining. Developing techniques that enable neural networks to generalize and transfer their knowledge effectively will be crucial for their future applications in real-world scenarios. 12.3.5 Energy Efficiency. As neural networks become more complex and require larger computational resources, energy efficiency becomes a significant concern. Training and running neural networks can be computationally intensive and energy-consuming processes. Finding ways to optimize the energy efficiency of neural networks, such as developing specialized hardware or algorithms, will be essential to reduce their environmental impact and make them more accessible for a wider range of applications. 12.3.6 Ethical and Social Implications. The rapid advancement of neural networks also raises important ethical and social implications. Issues such as bias, fairness, transparency, and accountability need to be addressed to ensure the responsible and ethical use of neural networks. Bias in training data can lead to biased decisions, and lack of transparency can make it difficult to identify and rectify these biases. Additionally, the impact of automation on jobs and the potential for algorithmic discrimination need to be carefully considered. It is crucial to develop frameworks and guidelines that promote fairness, transparency, and accountability in the development and deployment of neural networks. 12.3.7 Collaboration and Interdisciplinary Research. Addressing the challenges and harnessing the opportunities in the future of neural networks will require collaboration and interdisciplinary research. The field of neural networks intersects with various disciplines such as computer science, mathematics, neuroscience, psychology, and ethics. Collaborative efforts between researchers from these diverse fields can lead to innovative solutions and a deeper understanding of neural networks. Encouraging collaboration and fostering interdisciplinary research will be crucial for pushing the boundaries of neural network technology. 12.3.8 Democratization and Accessibility. Finally, an opportunity in the future of neural networks lies in democratization and accessibility. As neural networks become more prevalent, it is important to ensure that their benefits are accessible to a wider audience. This includes developing user-friendly tools and platforms that make it easier for non-experts to utilize neural networks, as well as addressing issues of bias and fairness to ensure that the benefits of neural networks are distributed equitably across different communities and populations. In conclusion, the future of neural networks holds both challenges and opportunities. Scalability, interpretability, data privacy, generalization, energy efficiency, ethical implications, collaboration, and accessibility are some of the key areas that need to be addressed. By tackling these challenges and embracing the opportunities, we can unlock the full potential of neural networks and pave the way for a future where they play a transformative role in various aspects of our lives. 12.4 Implications for Society and Industry. Artificial neural networks have revolutionized various industries and have had a profound impact on society. As these networks continue to advance and become more sophisticated, their implications for society and industry are becoming increasingly significant. In this section, we will explore some of the key implications of neural networks and discuss their potential benefits and challenges. 12.4.1 Automation and job displacement. One of the most significant implications of neural networks is the potential for automation and job displacement. As these networks become more capable of performing complex tasks, there is a concern that they may replace human workers in various industries. Jobs that involve repetitive tasks or data analysis, such as manufacturing, customer service, and data entry, are particularly vulnerable to automation. While automation can lead to increased efficiency and productivity, it also raises concerns about unemployment and income inequality. As neural networks continue to evolve, it is crucial for society to find ways to adapt and ensure that the benefits of automation are shared equitably. 12.4.2 Enhanced decision-making. Neural networks have the potential to greatly enhance decision-making processes in various domains. By analyzing vast amounts of data and identifying patterns, these networks can provide valuable insights and predictions. In fields such as healthcare, finance, and marketing, neural networks can help professionals make more informed decisions and improve outcomes. However, relying solely on neural networks for decision-making raises ethical concerns. It is essential to ensure that these networks are transparent, explainable, and free from biases. Additionally, human oversight and critical thinking should always be incorporated to avoid blindly following the recommendations of neural networks. 12.4.3 Personalization and customization. Neural networks have enabled personalized and customized experiences in many aspects of our lives. From personalized recommendations on streaming platforms to customized product suggestions on e-commerce websites, these networks have transformed the way we interact with technology. By analyzing user data and preferences, neural networks can tailor content, products, and services to individual users. This level of personalization can enhance user satisfaction and engagement. However, it also raises concerns about privacy and data security. It is crucial for society to establish robust regulations and safeguards to protect individuals' privacy while still benefiting from the advantages of personalization. 12.4.4 Healthcare and medical advancements. Neural networks have the potential to revolutionize healthcare and medical research. By analyzing medical data, such as patient records and imaging scans, these networks can assist in diagnosing diseases, predicting outcomes, and developing personalized treatment plans. The use of neural networks in healthcare can lead to more accurate diagnoses, improved patient outcomes, and reduced healthcare costs. However, there are challenges to overcome, such as ensuring the privacy and security of patient data, addressing biases in training data, and maintaining the trust of healthcare professionals and patients. 12.4.5 Ethical considerations and bias. As neural networks become more prevalent in society, it is crucial to address ethical considerations and biases. Neural networks are only as good as the data they are trained on, and if the training data is biased, the network's decisions and predictions may also be biased. To mitigate bias, it is essential to ensure diverse and representative training data and implement fairness measures during the training process. Additionally, transparency and accountability in the development and deployment of neural networks are crucial to building trust and addressing ethical concerns. 12.4.6 Environmental impact. The increasing use of neural networks and the demand for computational power have environmental implications. Training and running neural networks require significant computational resources, which consume a considerable amount of energy. This energy consumption contributes to carbon emissions and environmental degradation. To mitigate the environmental impact, researchers and industry professionals are exploring energy-efficient hardware and algorithms. Additionally, optimizing neural network architectures and training processes can help reduce energy consumption and make neural networks more environmentally friendly. 12.4.7 Collaboration and regulation. The development and deployment of neural networks require collaboration between various stakeholders, including researchers, industry professionals, policymakers, and ethicists. Collaboration is crucial to ensure that neural networks are developed responsibly, ethically, and in a manner that benefits society as a whole. Regulation also plays a vital role in addressing the implications of neural networks. Clear guidelines and standards can help ensure the responsible use of neural networks, protect individuals' rights, and prevent misuse or abuse of this technology. 12.4.8 Education and skill development. The widespread adoption of neural networks necessitates a focus on education and skill development. As jobs evolve and new roles emerge, individuals need to acquire the necessary knowledge and skills to work alongside neural networks effectively. Educational institutions and training programs should adapt to include courses and programs that teach the fundamentals of neural networks, their applications, and their ethical implications. Additionally, ongoing professional development and upskilling initiatives can help individuals stay relevant in a rapidly changing job market. In conclusion, the implications of neural networks for society and industry are vast and multifaceted. While these networks offer numerous benefits, such as automation, enhanced decision-making, and personalized experiences, they also raise concerns about job displacement, biases, privacy, and environmental impact. It is crucial for society to address these implications through collaboration, regulation, education, and ethical considerations to ensure that neural networks are developed and used responsibly for the betterment of society.